Hi, my name is Mosh Hamedani, and I'm really pleased to be your instructor in this C# Intermediate course. This course is the second part of my C# series. In the first part, I talk about the fundamentals of C# and procedural programming. In this course, our focus is purely on classes, interfaces, and object-oriented programming. Note that object orientation is a complex topic, and it takes a lot of books, videos, and years of thinking to really master it. But this course opens your eyes to the object orientation. You will learn the principles of object orientation, including encapsulation, inheritance, and polymorphism. I will show you why encapsulation is so important and how it helps writing robust code. I'll talk about inheritance. Inheritance is a way to reuse code, but unfortunately, it's misused a lot by a lot of amateur designers and developers. I will show you the problems with inheritance, and then I will introduce you to the concept of composition as a more flexible way to reuse code. Then I will talk about polymorphism. I will show you how you can take a piece of code that has a lot of if, else, and switch statements and refactor it into an object-oriented style. You will learn how you can change the behavior of an application by extending it. So instead of changing the existing code, which may affect parts of your application, you create new classes that change the behavior of your application, and this is extremely powerful. And finally, I'll talk about interfaces. Unfortunately, there is a lot of wrong information about interfaces in the community. In fact, when I started learning C# back in 2002, the book I read, which was actually published by Microsoft, gave me the wrong information about interfaces. And for that reason, I was confused about interfaces for years. I was taught that interfaces are used to implement multiple inheritance in C#, and that is absolutely wrong. It took me years to really understand interfaces, and that's the reason I decided to create this course for you. So whether you're brand new to the concept of classes, interfaces, and object-oriented programming, or you have some experience, you're going to get a lot out of this course. I will show you how interfaces improve the testability and extensibility of your application. So you will see an introduction to unit testing and how we can use interfaces to improve the testability of our application. I've been really excited about making this course, and I hope you become a better developer after watching this course. That's enough introduction for now. Let's get started. Okay, that's the part that I hate to talk about because in my culture, we are taught to be modest and not to talk about ourselves. But you, as my student, might want to know who your instructor is and whether they're qualified to teach the course you have taken. So here is my story. I started programming at the age of 7 with a Commodore 64 and totally fell in love with it. Since then, I continued learning more and more about programming. So I've dedicated pretty much most of my life in learning and practicing programming. In my high school years, I was more of a C and C++ programmer. And later, in 2002, when .NET version 1 was released, I shifted to C# and .NET platform entirely. So I have 12 years of experience designing and developing applications with C#, and at the time of recording this, I'm also a full-time C# developer. I'm also a Microsoft certified technology specialist, application developer, and professional. In terms of my educational background, I have a Bachelor of Science in Software Engineering and a Master of Science in Network Systems. Recently, I started my YouTube channel called Programming with Mosh. So if you'd like to learn more, subscribe to my channel. Now you're wondering, Mosh, do you have a life outside programming? Of course I do. When I'm not programming, I'm playing jazz piano, doing Latin dancing, or photography, as well as cooking. I love cooking. Okay, that's it about me, and I will see you in the next lecture. Okay, before we move on to the next section, I want to spend a couple of minutes and talk about something very important. I want to make sure I've set the expectation right before you get started. So please watch this video to the very end. I've done my best to produce this course with all the materials you need. But as you work through the course, there are times that you might have questions. Here we have a discussion board where you can post your questions. But remember, this discussion board is mainly for students to help each other, not as a medium for me to answer every student's questions. Because even though I would love to help each of you individually, unfortunately, that's not possible. Because given the volume of students I have on Udemy and the subscribers on my YouTube channel, it's really hard to answer everyone's questions. And believe it or not, this gets more challenging every single day. I'm sure you would feel the same if you were in my shoes. Remember, just like you, I'm a regular person, and I have limited time per day. If I answer everyone's questions, I have to literally stop producing new content. And I'm sure that's not what you want. I've got several thousand students who are constantly emailing me and asking for new content. Mosh, can you do a course on this? Can you write a blog post on that? So I just want to set the right expectation. I will answer your questions when I get a chance, but this is more of a nice thing to have, and it's not something you should expect as part of this course. Because what you have paid for is purely for the material, proper structure that leads you from zero to hero, so you don't have to jump from one tutorial to another. Plus the exercises that I have carefully designed to ensure the best learning experience for you. That's what you're paying for. And this is not a private one-on-one class. And I want to make sure we're on the same page before you get started. Now you may say, but Mosh, there are other instructors who are very active in the discussion board and they answer every single question. I don't know what they are doing, how many courses and students they have, but maybe they have superhuman power. Unfortunately, I don't have. Now, all that aside, if you have questions, remember a lot of times you can get your answer much faster if you just simply Google it. I've seen a lot of questions on the discussion board that have an answer on the first page of Google. Also, in particular, I do not answer questions that are about some code not working on your machine or you're getting a runtime error. Because if you want to be a real coder, you need to troubleshoot these issues yourself. You cannot expect others to fix the compile time or runtime issues with your code. So I do not answer these questions whatsoever, purely to help you become more independent and better at solving these problems on your own, so you can be successful in your career. All right, that's all I wanted to talk about. I hope you're on the same page. Now let's move on to the next section. Okay, we're going to start our journey by learning about classes. In this lecture, I'm going to introduce you to the basics of classes. I'm going to show you a real-world example of classes and why we need them. Then I'm going to talk about what is an object and how it's different from a class. And finally, we'll talk about static members. So what is a class? A class is simply a building block of a software application. So in the real world, an application consists of multiple classes, each responsible for a particular behavior in the application. And overall, all these classes together will provide the behavior expected from the application. Let's take a look at a real-world example. We all are familiar with the concept of blogs and posts. Let's say we would like to implement a web application as a blog engine. With a typical layered architecture, our software application consists of at least 3 layers: presentation, business logic, which is also referred to as domain layer, and data access, which is also referred to as persistence layer. In each of these layers, we can have classes, each responsible for something particular. For example, in the presentation layer, we can have a class like postView, which is purely responsible for displaying a post to the user. In the business logic or domain layer, we can have the concept of post itself. And finally, in the data access or persistence layer, we can have a class like post repository, which knows how to save a post to the database or load it from a database. A real-world application often consists of hundreds or even thousands of classes collaborating with each other. So for you as a C# programmer, it's absolutely crucial to understand classes and how to use them effectively to build a maintainable, clean, robust, reliable application. This lecture is pretty basic, but as we progress in this course, in every lecture and in every section, I teach you something new about classes. By the end of this course, you're going to learn a lot of materials about how to use classes and interfaces to build loosely coupled, extensible, and maintainable applications. So let's continue our journey. Now we know a little bit about a class. So it's a type that we developers define and give it a responsibility depending on the kind of application we're building and the layer that class belongs to. But what is inside a class? A class essentially has 2 parts: data, which is represented by fields, and behavior, which is represented by methods or functions. Here is how we illustrate a class in UML, or Unified Modeling Language. UML is a graphical language for representing classes and their collaboration. And we use that as a communication tool as part of building software. So in UML, a class has three parts. The first part is the name of the class. Then here are the fields or attributes of that class, which represent data about that class. And finally, we've got the methods or functions, which provide some behavior. So in this example, our person class has fields like name, age, height, and weight, and it has methods like walk, talk, eat, and sleep. Let's take a look at another example. We talked about blogs and posts. So a blog post can have attributes or fields like title, description, and date time. And it can have methods like publish, like, or comment, which receives a message. A term that is often used with classes and sometimes used interchangeably is an object. But an object is fundamentally different from a class, yet a lot of developers, including myself, sometimes use the word object to refer to a class. But an object is essentially an instance of a class that resides in the memory. So back to our person example, if person is a class, we can have objects like John, Mary, and Scott. These are instances of that person. The person class or the person type defines the blueprint from which we can create objects. At runtime, these objects in the memory talk to each other, and as a result, we get the behavior expected from the application. Now let's see how we can declare a class in C#. Here's a basic syntax for declaring a class. Public and class are keywords, are reserved keywords in C#, and that's why I've indicated them with blue. Public is what we call an access modifier, and that's something you're going to learn later in this section. So for now, don't worry about it. Each class should have a name or an identifier, like person. In terms of naming convention, in C# we use Pascal case to name our classes. What is Pascal case? In Pascal case, the first letter of every word should be uppercase. We also have camel case, in which the first letter of the first word should be lowercase, but the first letter of every word after that should be uppercase. In C# we use camel case when naming parameters of methods, as you will see later in the section. So back to the declaration of our class. The class can have fields and methods, which we refer to as members of that class. We put members inside these curly braces here. We can declare a field for this class and call it name. Similar to the class, we start with an access modifier, in this case public, then the data type for that field, and an identifier. In the real-world applications, we shouldn't declare fields with public. This is purely for taking you on a step-by-step journey without confusing you with a lot of details along the way. As we progress in this section, you will find the best way to declare fields. Okay, now let's see how we can declare a method in this class. Very similar. So we start with an access modifier, and here is the signature of the method. So a method can have a return type. In this case, void means it doesn't return any value. Then it has an identifier, and here in brackets we can put any parameters that method may need. Inside that method, we have the code. And here we can access any of the members of that class. So in this example, I'm simply using console.writeLine to display the name of that person on the console. Okay, now that we have a class, let's see how we can create an object or an instance from it. To do that, we use the new operator. So we start with the type of the class, in this case person, we give it an identifier, and then we use the new operator along with the name of the class to initialize an instance of that class. Note that here we are using camel notation for naming the person object. A shorter way to write this code is to use var. Var is a C# keyword, and the reason we use that is to save us from typing the full name of a class, because sometimes the name of the class might be quite a few characters. Plus, as you see, it's a little bit of duplication to repeat the name of the class in two places. So we use the var keyword, and the compiler automatically knows that this person object is of type person. Now that we have an object, we can access members of that object, like accessing the name field and giving it a value. Or we can call one of its methods. Before we start coding, let's talk about class members. In C#, we have two types of class members. We have instance members and static members. An instance member is accessible from an object. You have already seen that before. So we create a person object and then call the introduce method on the object. But we also have static members, and a static member is accessible from the class, not an object. An example of that is console.writeLine. So console is a class and writeLine is a static method. So we don't have to create an instance of console using the new operator in order to call writeLine. Now you may wonder, why do we use static members? Basically, we use them to represent concepts that are singleton. That means we should have only one instance of that concept in the memory. Think of the concept of the current date time. We should have only one place in the memory where we know the current date time. It doesn't make sense to have different objects, each telling us that current date time is a different value. Another example is console.writeLine. When we run a console application, basically we have only one console, and that's why the console class and all its members are defined as static. To declare a member as static, all you have to do is to use the static keyword after the access modifier. You can use static on any members of a class. Okay, that's enough theory. Let's open up Visual Studio and do some coding. Okay, here I've got a console application in Visual Studio. And that's where we're going to do all the coding for this course. We're not going to get into the complexity of Windows applications or web applications or mobile apps. We just want to learn about classes, interfaces, and object-oriented programming. What you learn here, you can always apply in any kind of application you're going to build. Okay, now let's start creating our first class. So we create a class by public class. Let's give it a name like person. Let's define a field for it. So public string name. Again, for now, we're going to use public until we get to the lecture about access modifiers. And then we're going to learn a better way to define fields. And let's create a method called introduce. I want this method to take a parameter, and that's the name of the other person that this person is going to introduce himself to. So let's say introduce to, and here we use the console class, the writeLine method. Hi, 0, I am 1. Basically, what we have here is what we call a format string. So it's like a template. And here are parameters that we will fill by some values. So I want the first parameter to be filled by the value of 2 argument. And the second one is going to be the name field stored in the class. Now that we have this class, let's create an object from it. So we go to the main method. We can either go person equals new person, or a shorter way is to use var. So with var, we'll let the compiler figure out what is the type of this person object. Well, compiler knows it's assigned to a new person object here. So when you hover your mouse over var, you see the tooltip says person. Now we can assign this person name. Person.name equals, say, John. And then we can call the introduce method and pass another name as an argument. Say, introduce yourself to Mosh. Now, if you run this application, you see, hi Mosh, I'm John. Now let's take this to the next level. Let's say we would like to create a person object from a string. What we can do is to create a parse method. So let's go and define a parse method here. The parse method should take a string and return a person object. So person parse string so str. Basically, what we need to do here is to create a person object, set the name field based on the str argument here, and then return that. So var person equals new person. We set the name to str and finally return that person. Now, the interesting thing here is if you want to use this parse method, we have to use it on an object because it's an instance method. So that means I can go here and say person.parse and give it a name like John. and that returns a person object. So let's call it P. And we can get rid of this name here for now. See, it's a little bit weird. We have to create a person object first and then call the parse method to return a person object. It just doesn't make sense. That's where we use a static modifier. So we can declare this parse method as a static. And this way, we don't have to create a person object first in order to parse a string. So we can simply change this code to use the person class. We parse that string, and now we have a person object. And finally, we can call the introduce method on it. Let's run the application. We get the same result. So that's a use case for using a static member. A static member is only accessible from the class and not an object. That's pretty much it for this lecture. In the next lecture, we're going to learn about constructors. I hope you enjoyed this lecture, and thank you for watching. Okay, we got to constructors. What is a constructor? A constructor is a method that is called when an instance of a class is created. Why do we need a constructor? The intention is to put an object in an early state. That is, to initialize some of the fields in the class. Here is how we declare a constructor. So as you see, we have a class called customer, and this class has a constructor as you see here. A constructor has the exact same name as the class, and that's a requirement. If you change this name, the compiler or the runtime will not treat this as a constructor. Also note that constructors, unlike other methods, do not have a return type, not even void. Here in this method, we can do any kind of initialization that is required. Note that we don't always have to use a constructor, but if we need to initialize an object upon creation, that's where we put our code. In this example, we have what we call a parameterless or a default constructor. So this constructor has no parameters. If you don't define a default or parameterless constructor for your class, the C# compiler creates one for it. You're not going to see it, but it will be in the IL or intermediate language code that will be the result of the compilation. That constructor doesn't do anything. It just initializes the fields of the class to their default values. What are those default values? For any kind of numbers, it sets them to 0. For Boolean types, sets them to false. For any other kind of reference types like strings or any other objects, sets them to null. And for characters, sets them to an empty character. Here is another example of a constructor. In this example, we have a parameter here. So we get the name of the customer and we set the name field as you see here. Note the use of the this keyword. This is a keyword that references the current object. Why do we need that here? Look, here we have two identifiers that look very similar. We have this name field in the class and this name parameter in the constructor of this class. They both have the same spell, but are using different naming conventions. This parameter here is using camel case, so the first letter of the first word is lowercase. The name field here is using Pascal case, so the first letter of the first word is uppercase. It is possible that sometimes we make a mistake, and in the assignment operator here, we put the wrong variable on the wrong side of the equation. In this example, we are passing this name here, and we simply copy that to this name field here. And that's the right way to do it. But imagine what it would look like if it was the other way around. It wouldn't make sense. That's why we use the this keyword here to make sure what we have on the left side of the assignment operator is a member of the class, in this case, the name field here. So what we get from the outside, which is in this case the constructor parameter, will be copied to the name field. Okay, with that constructor, when we create a new instance of customer, we can supply a name here. At this point, the constructor will be called, and the string that is passed here will be copied to the name field. We have a concept called constructor overloading. Overloading means having a method by the same name but different signatures. What do I mean by a method signature? A signature is what uniquely identifies a method. That is its return type, its name, and the types and numbers of its parameters. In this example here, we have 3 constructors, so we have overloaded the constructor for this class. Each constructor, as you see, has a different signature. So the first one takes no parameters. The second one takes one parameter of type string. The third one takes one integer and one string as parameter. Note that the names here do not matter, but the data types for the parameters and the order of them is important. So we cannot have 2 constructors with the exact same signature. Now you might wonder, why do we need to overload constructors? The reason for that is to make initialization of this class easier. Sometimes we may know only the name, so we may use this constructor when creating an instance of this class. Sometimes we may know both the ID and the name, so we use this one. Or sometimes we may know neither of these parameters, so we may use this constructor here. Okay, let's start coding and see constructors in action. Okay, let's start by creating a customer class. So, public class customer. Now we declare a field. Public integer ID. And another one, public string name. Before I move on, I need to clarify something here. In the real-world applications, we do not declare fields with the public access modifier as you see here. This is just because I want to take things in a step-by-step fashion. When we get to the lecture about properties, you will see a better way to declare fields. For now, let's just keep things simple and learn everything in a step-by-step fashion. Okay, now let's put this customer class in a separate file. Here I'm using ReSharper. If you don't have ReSharper, I highly recommend you to purchase a license for it because it really helps you with your coding. Note that I'm not a ReSharper affiliate and I don't get a penny from promoting their product. I just believe ReSharper takes coding to the next level. It makes it much easier and much faster. Alright, let's put this class in a separate file. So I put the cursor here and note this little icon here. That is used for refactoring. That means changing the structure of the code without changing its functionality. So here I press Alt and Enter, and it pops up this context menu here. The first item says move to another file to match type name. So I just press Enter and note that now we have a separate file called customer.cs, and this file is added to Solution Explorer. So if I didn't have ReSharper, I had to go here, right click, and then go to add, and hang on, you don't see that here in the screen. So I put the Solution Explorer to the left side. Okay, so right click, add new item or class, which would open up this dialog box here, and then here we had to type customer.cs. It's really not a good and fast way, because as a professional programmer, you don't want to switch to mouse while you're coding. You should learn to do everything with keyboard. That's much easier and faster. So let's not worry about creating a new file and use ReSharper from now on. I put this Solution Explorer back to where it was. There you go. All right, now let's go to the program CS here in the console application and create a new instance of this customer. So customer equals new customer. Or a better way is to use var instead of customer, because note that here we are repeating this customer word twice, and that makes the code slightly cluttered. So we can just use var here and let the compiler figure out that customer is of type customer. So the code looks a little bit cleaner now. All right, now I want to show you the effect of the default constructor that the C# compiler creates for us. Note that here in the customer class, I did not create a constructor. But I told you earlier in the slides that the C# compiler creates one for us. So let's see what happens. Let's display the fields of this customer class on the console. So console.writeLine, customer.id, and console.writeLine, customer.name. Note that the way I typed console.writeLine was via what we call a code snippet, which is much faster. So I didn't type console.writeLine. I just typed CW and pressed tab. This is what we call a code snippet. It's a quick way to write code. There are many code snippets in C#, and I have explored many of them in my course Double Your Coding Speed that you can find on Udemy. So let's move on for now. Okay, now let's put a breakpoint here. We can put a breakpoint using F9. And we run the application in the debug mode using F5. Okay, I'm going to put a watch on the customer object here. So customer, let's expand this. Note the default values assigned to these fields here. So ID is an integer, and the default value for the integers or any other kind of numbers is 0. Name is a string, and the default value for strings or any other kind of reference types is null. So this happened by the default constructor that the C# compiler created for this class. Okay, now let's declare a constructor and see how we can initialize this field upon instantiation of a customer. So I stop the debugger using Shift and F5. We go to the customer class. To do that, I simply press Ctrl and Tab. Look, we got the open windows here in Visual Studio. I didn't have to go and grab my mouse, go to Solution Explorer and double click customer. All right, now here, let's declare a constructor. To declare a constructor, there are two ways. The slow way is to type public and the name of the class and the curly braces. What is the fast way? You type ctor, as in short for constructor, and note the icon for the code snippet here. So that's a code snippet. Here we can press the tab. There you go. We got the constructor. So this is how I want you to code. I don't want you to type every letter. As a fast coder, you should know all your shortcuts. You should code like a ninja. Okay, now let's give a parameter to this constructor. So I go here and let's say integer ID. And here we need to copy that to our ID field. So I type in this dot. Note here are the members of this class. So here's our ID field equals ID. Now let's overload this constructor. So I'm going to create another one with a different signature. Again, ctor, we got here. Now this time I want to add two parameters, int ID and string name. Okay, now let's initialize them. This.id equals ID, this.name equals name. Now if we go back to our program class, again using Ctrl and Tab, here note that we got a red underline. And that's because the compiler cannot find a default constructor that is parameterless. So we can no longer create a customer object using this constructor because it doesn't exist. So what does this mean? That means because we created two custom constructors, the compiler will no longer create that default or parameterless constructor. So if we still want to have this freedom to create a customer object without supplying any parameters upon instantiation, we need to go back here and create a default or parameterless constructor. So ctor, that's it. In this case, I'm not doing anything here. Back to program. Note that the red underline is gone. But also, when we open the bracket here, note that here we have three overloads for the constructor. One is without any parameters, one takes an integer, and one takes an integer and a string. Let's use the third one. So I set the ID to 1 and the name to John. Now we run the application. Note that ID is initialized to 1 and name is initialized to John. And that's the intention of using constructors. Okay, now let me tell you a best practice. Let's get back to our customer class. See, in this case, our customer class has only two fields. And we have created different variations of these constructors here for initializing these fields. What if we had 5 other fields here? Would you go and create 7 other kinds of constructors for initializing each of these fields? No, definitely not, because that would create a lot of clutter in the class. We only use constructors in classes in situations where we really want to initialize that object to an early state that is really important for that object to perform. In this simple example we have here, it doesn't really matter whether the customer object has an ID or not. Same goes for name. We can always create a customer back here. Let me remove these two parameters. We can always create a customer object and then set the ID here. It's not the end of the world, John. But there are cases where you really have to initialize an object to an early state. What is an example of that? Let me show you. So I want to create a new class. Let's call it order, public class order. Let's not worry about the fields in this class for now. So I'm going to put this in a separate file, put the cursor here, Alt and enter, enter. Done. Now go back to the customer. In the customer, we want to create a list of orders. So we use the list class, public list of order, and we call it orders. In case you're not familiar with this list is a generic class that takes a parameter. This is what we call a generic parameter. So it represents a list of objects, and this parameter here specifies the type of those objects. So in this list, we can store objects of type order. Note that this list is declared in the system.collections.generic namespace. And here, because I'm using ReSharper, as I was typing list of order, ReSharper automatically added that using statement on the top. If you're not using ReSharper, you have to manually add this statement. Okay, let's move on. As a rule of thumb and as a best practice, whenever you have a class, like here, and that class has a list of objects of any type, always initialize that list to an empty list. What I mean by that is, in the default constructor here, we go and type orders equals new list of orders. Now you might wonder why. I think the best way to explain it is by showing what would happen if we didn't do this. So let me just comment this out. To do this, with ReSharper, you can press Ctrl and slash. If you are not using ReSharper, Ctrl K, Ctrl C. All right, let's go back to the program. Let's add a new order for this customer. So I'm going to create var order equals new order. Now let's say customer.orders.add this order. If we run the application now, it's going to crash. We got an exception, a null reference exception. The reason this happened was, let's close this, because orders was not initialized, and by default, because it's a reference type, it was set to null. So when we call the add method on a null object, we get null reference exception, which is a very bad thing. That's something we need to avoid at all times. Now, an amateur programmer may solve this problem by doing something like this here. So saying customer.orders equals new list of orders. That may look like a solution, but it's actually a bad solution. In fact, I wouldn't even call it a solution. It's a hack. It's a patch. Why? Because here, in this main method here, we should not be responsible for initializing that orders list to an empty list. It's not the responsibility of this class here. This class just wants to add an order to this customer. It's the responsibility of the customer class to make sure that its orders field is initialized to an empty list, and it's not a null object. If we take this responsibility from this customer class and initialize that orders field somewhere else, then it's going to be a problem. Because everywhere in our code we are going to use a customer object, we have to remember to initialize that orders field. Okay, so I'm going to remove this line here, and go back to the customer class. In the default constructor, I want to make sure that the orders field is always initialized to an empty list. So that's the rule of thumb. Whenever you have a class and that class has a list of objects, make sure that list is always initialized. Now we have another problem here. If we use this constructor here, everything is good. The orders field is initialized. But what if we use either of these constructors here? Orders is going to be null. Well, we can go and copy paste this line into these constructors, but it's not really a good way. What if we had 3 other fields here that they all were lists? So we had to copy paste 3 lines of code into each of these constructors here. Is there a better solution? Of course there is. We can use this keyword. Let me show you how it works. So here in this constructor, upon declaration, I would put colon this and put the brackets like this. This means when this constructor is being called, first it's going to call the constructor without parameters. So before this line is executed, this constructor is going to be called, which will initialize the orders field, and then we get into this constructor here. Let me show you another example to make sure we really nail it down. So using a similar technique, I can go to this constructor and colon this. Note that we have 2 constructors here now we can call. One is the default parameterless constructor. One is the one that takes an ID. I'm going to pass this ID that is coming here into this constructor and then get rid of this line here. What this means is when we use this constructor to initialize the customer object, first it's going to call the constructor that takes the ID parameter. So we're going to go here. And note that here, before this code is executed, we're going to go here. At this point, the orders field will be initialized. Then we get back here, the ID will be initialized, and finally we'll get back here, the name will be initialized. So what I want you to learn here is that we can use this keyword and specify any of the other constructors we would like to pass the control to. Now here we have a simple example, and it's kind of okay to pass the control from this constructor to this one to this one. But in general, this is not considered a good practice because it makes the control flow a little bit complicated. For example, imagine someone else had written this code and you had to maintain it. You look at this constructor and then you had to look somewhere else and then you had to look somewhere else. It's a little bit ugly. So what I suggest to you is keep the using of this in this way to a minimum and only define a constructor when you really have to initialize some fields of your class. In this example, I explained to you that we really have to initialize this orders field here. So we created a default constructor. I can argue that these two are really redundant and they're just making the code a little bit ugly and hard to maintain. So it's okay to remove them, but I'm just going to keep them here because I wanted you to learn a few concepts here. One is the default and parameterless constructor. Another one is the concept of overloading constructors. That means we have 3 different constructors. Each has a different signature. And how we can use this keyword to pass the execution to another constructor in this class. Well, that's pretty much it for this lecture. I hope you enjoyed it and thank you for watching. Okay, object initializers. In the last lecture, we learned about constructors. You know that we use a constructor to initialize an object and put it in an early state. In C#, there is also another way to initialize an object, and that is using an object initializer. An object initializer is simply a syntax for quickly initializing an object without the need to call one of its constructors. Why do we need that? Simply to avoid creating multiple constructors. Let me show you an example. Imagine we have this person class with a bunch of fields. Now, this is a very simple example. We only have 4 fields here. In a real-world application, you might have a few more fields. Now, with this class, if we want to create constructors for initializing various fields, we may end up with a class like this. So as you see here, I have 4 constructors. The first one takes only an ID. The second one takes an ID and a first name. The third one takes an ID with first name and last name, and so on. So you see there are so many different combinations. And this is what we used to do in C# before object initializers were introduced. So as you see, writing code like that is messy and easily becomes out of control. So object initializer came to solve this problem. With an object initializer, we don't need any of these constructors. We can simply initialize a person object like this. Notice curly braces here. I'm not calling one of the constructors of the person class. This syntax you see here is what we call object initialization syntax. So basically you specify the name of properties and assign them some initial value. Note that behind the scene, when you initialize an object like this, the default or parameterless constructor is going to be called, and then any properties you set here are going to be initialized. So with this way, we can reserve constructors for scenarios where we really need to use them, as I explained in the last lecture. So an object cannot behave without being passed some initial values. That's pretty much what you need to know about object initialization syntax. In the next lecture, we'll take a closer look at our methods and their parameters. I hope you enjoyed this lecture, and thank you for watching. Okay, we got to methods. At this point, you should know what a method is, so I'm not going to review that again. But in this lecture, I'm going to cover some additional details about methods. I'm going to start by explaining the concept of signature for methods. Then I'm going to talk about method overloading, which you should already be familiar with because I already talked about in the lecture about constructors. But here you're going to see another example of overloading methods, which can be useful. Then I'm going to talk about 3 modifiers that we can apply to method parameters, and there are params, ref, and out. Out of these 3 modifiers, params is the only one that I consider useful. In my opinion, ref and out are bad decisions made when designing the C# language. They're code smells, and a lot of developers have the same opinion. Initially, I didn't want to include them in this course because I don't want to teach you bad things, but because I wanted my course to be comprehensive, I decided to include them here. Plus, there are areas in the .NET framework where you have to use the out modifier. So I want you to know how to use them, even though I'm not going to advise you to use out modifier when designing your classes and methods. We'll see the reasons later in this lecture. So let's get started. What is the signature of a method? The signature of a method consists of its name and the number and type of its parameters. So in this example, you see we have a point class that has a method called move. I have highlighted the areas where make up the signature of this move method with yellow. So the name and the type and number of parameters. A concept that goes hand in hand with the signature of a method is overloading. So basically overloading means having a method with the same name but different signatures. Look at this example here. We have a point class with 3 move methods. Imagine this point represents a point on the screen. And we would like to move this to a different location. So we can have 3 overloads of the move method. One that takes 2 parameters of type integer, which represent an x and y. Another overload can take a point parameter. And with this technique, we make it easier for the consumer of this class to choose the right overload. Maybe sometimes we have 2 integers and it's more handy to call the first method here. In other times, we might have a point object and it would be easier to use the second overload. And also here we have a third overload that takes a point and a speed, which can create some kind of animation while moving the point from one location to another. You don't always have to overload your methods, but if there are cases where you see you can improve your code and make it easier for the consumer of your method, overloading is a technique in your toolbox. Okay, now that you understand the concept of method overloading, take a look at this calculator class here. This class has at least 3 overloads for the add method. The first one takes 2 parameters, the second one takes 3 parameters, and the third one takes 4. But as you see, this is not an efficient way to overload the add method. What if we wanted to add 10 numbers together? Then we would have to overload the add method 10 times. And that's a code smell. Is there a better way to achieve this? Of course there is. The first step to make this code better is to use an array. So instead of overloading the add method 10 times, we can declare it only once and have it receive a parameter of type integer array. With this declaration, we can use the add method like the example you see here. While this works perfectly fine, there is just a slight problem here. And the problem is every time we want to pass a number of arguments to this add method, we have to create and initialize an array. So we have to use the new operator and the int array notation. It's not a big deal, but there is a simpler way to do that. And that's when we use the params modifier. So we can change the declaration of our add method to include the params keyword here, just before the integer array. With that, we can call this method in a couple of ways. We can use it in the traditional form, so we pass an integer array, or we can simply pass a varying number of arguments here. We don't need to create and initialize an array. And that's simpler. Again, this is not something that you use all the time, but if you have situations where your method might need a varying number of parameters, you can use the params modifier to make it easier for the consumer of that method to call that method. Okay, now let's take a look at the ref modifier. This is probably the only example in this course where I'm going to use names like my class and my method because I really don't like this kind of teaching. If you have noticed, I try to use real-world examples that make sense as opposed to abstract names like my method, my class 1, 2. It just doesn't make sense. Anyway, because the ref and out modifiers are what I call a code smell, I couldn't think of a real-world example to demonstrate this concept here. So let's just imagine this my method here takes an integer and whatever we pass, it adds 2 to that integer. Now take a look at this example here as what we would write to call that method. Now I have a question for you. Here we have set a to 1. We call my method and pass a. What do you think would be the result of a after returning from this method? Is it going to be 3? No, it's going to be 1 because a is a value type. And that means when we pass a to a method like the one you see here, its value is being copied. So the int a that we have here is a local copy of a that will be relevant to this method here. It will not affect the original a that we had here. We can change this code by including a ref modifier to our method. And note that here I changed the name of the class and its method from my class and my method to weirdo and do a weird thing because it just is weird. So with this change, if we call this method and also include the ref modifier here, the original a that we have here will be passed to this method and its value will be modified. So after we return from this method, value of a is going to be 3. I'm completely against this concept. I think it's a code smell and I want to make sure that you're never going to use this. But if there are classes written by other people or perhaps somewhere in .NET Framework where a parameter is defined with the ref modifier, I want you to know that in order to call that method, you need to specify the ref modifier here. Honestly, I can't remember on top of my head whether we have places in the .NET Framework where methods are defined with the ref modifier. But that's all I want you to know. Now let's take a look at the out modifier. Now, out modifier is slightly similar to the ref modifier in the sense that if a parameter is declared with the out modifier, as you see here, then in order for you to call that method, you also need to specify out when calling that method. But out is conceptually a little bit different from ref. What does it mean? That means with the out, this method can return a value to the caller. Now you might be wondering, couldn't we just return a value here instead of using void? Absolutely yes. But with the out keyword, we can have multiple parameters here and they all can return a value to the caller. And that's exactly where I say this is a code smell or this is a design smell of the C# language. Because if a method is going to return multiple values to the caller, it's better to encapsulate all these values into a separate class, which could be the return type of that method. So again, I want to emphasize, do not ever use the out modifier when designing your methods, but I included the out modifier here because there is one place in .NET Framework that you might be using sometimes, and that's where you have to use the out modifier, even though it's not a good choice, but I want you to be aware of that. Okay, enough theory, let's start coding and see all these concepts in action. Okay, let's start by creating a point class. So, public class point. This point represents a point on the screen. So it needs two fields, an X and a Y, and they both have to be an integer. So public int X, public int Y. And here we should create a constructor to initialize these fields. So ctor tab, we get two parameters, int X, int Y. And this.x equals X, this.y equals Y. Pretty simple. Now let's put this class in a separate file to clean up our code. So the cursor is here with resharper. We press Alt and Enter and Enter again. Now point is in a separate file. Now let's add a method to move this point to a different location. So public void move. We need two parameters, an X and a Y. And we simply change the value of our fields using these arguments. So this.x equals X, this.y equals Y. Now we can overload this method by creating another version of that takes a different signature. Maybe the other one takes a point object. Let's see how it works. So public void move. Here we pass a point object, that is the new location. And we use this object to change the value of our fields. So this.x equals new location.x. This.y equals new location.y. Now let's go to our program class. So we simply press Ctrl and Tab to switch between open windows. There you go. Let's create a point object. Var point equals new point. And I give it an X and Y, so 10 and say 20. Now if we call the move method, point.move, look, we've got two versions of this method. So there are two overloads. The first one takes a point object, the second one takes an X and Y. Sometimes in our program, we might just have two numbers, whereas other times we might have a point object. So by overloading this method, we make it easier for the caller of this method to pass arguments to this method. So let's try both versions. First, I pass a point object. Let's move it to 40 and 60. Now to ensure that everything is working, let's put the value of X and Y on the console. So CW tab, again, this is a code snippet. If you want to learn more of these fast coding techniques, I have a course called Double Your Coding Speed on Udemy, where I teach you lots of techniques to write code fast. So here in console.writeLine, we can say point is at, and here we pass the location. So point.x, point.y. Let's run the application with Ctrl and F5. Okay, point is at location 40 and 60. So our move method is working properly. Now let's extend its example, and this time use the other overload of the move method. So point.move. This time I want to move it to 100 and 200. So I use the second overload. Again, let's copy paste this line here and make sure everything is working. We run the application. Okay, so our point is moved twice, and now it's at the location 100 and 200. So this is how overloading works. But I want to show you that there is a problem with this code in terms of best practices. Let's get back to the point class. Okay, here we are duplicating the concept of setting X and Y. Now this is a very simple example, and we are just setting two fields. But sometimes in more complicated scenarios, it's not a good idea to repeat the same concept in two places. So what we can do is to make this move method call the other move method. This way, we set X and Y in only one place. So if there's a bug in our program, there's one place that we have to fix. Let's see how we can implement this. So here, I simply call the other move method, and I pass new location.x and new location.y. And we can get rid of these two lines here. Looks better, doesn't it? But there's still one more problem with this code. Can you spot it? And to give you a hint, it's here. There is one tiny problem here. The problem is, if we pass a null object here, this method is going to throw an exception. Let me show you what I mean by that. So we go to program. I'm going to change this line. So instead of passing a point object, I pass null. Let's run the application. There you go. The application crashed and we got a null reference exception. In case you are not familiar with exceptions, exceptions are .NET's way of error reporting. I've covered exceptions in full detail in my C# Advanced course that you can find on Udemy. So let's move on for now. We go back to the point class. Here we need to validate the argument that is passed in. So we make sure that it's not null. Otherwise, if we go null.x or null.y, we're going to get a null reference exception. We go if new location is null, we throw an argument null exception and pass the name of the parameter. What does this mean? First of all, throwing an exception is a way to report errors to the caller. So here, I use the throw keyword, and here I create a new exception object. An exception is just a class, and here we're just instantiating that class. And in the constructor here, I simply pass the name of the parameter that was null, in this case, new location. With this code, if new location is null, we're never going to get here. So the state of our class, which means the x and y, is not going to be changed. So this way, our point object will always stay in a valid state. The technique I have used here, as in validating this argument here, is called defensive programming, which is actually beyond the scope of this course. But basically, defensive programming improves the robustness of your code. Okay, now let's run the application and see what happens. Look, the application crashed again. But the difference is, this time we got an argument null exception as opposed to a null reference exception. So you may argue, how is it different? Well, it's better to get an argument null exception than null reference exception. Why? First of all, your application should always have a global error handling mechanism. The reason our application crashed here is because we don't have a global error handling or exception handling mechanism. I will show you how we can add that in a few seconds. But the point here is, when we get an argument null exception, we are immediately telling the caller of this method, that is this move method, that the value they have passed in is not a valid value. And as a result, no further actions will happen. That's the idea of writing robust code. If you get some invalid value, whether it's null or some value that is out of range, or maybe somewhere you don't expect a 0 or an empty string, then if you get that value and do operations on that value, you're taking your program to an unexpected state, which means some weird things may happen down the track. So the idea of defensive programming is to stop the program from getting into that weird or invalid state. Okay, now let me show you how we can improve this code by adding a global exception handling mechanism so the application won't crash. Let's get back to our program. So simply I add a try block here. You simply type try and press tab. Let me show you again. Try, tab. So again, this is a code snippet. You immediately get a try and a catch block. The code that may throw an exception should be placed in the try block. And if an exception is thrown, then this catch block will be executed. Don't worry about this throw keyword here. Just remove it. Again, I have covered the exception handling in more detail in my C# Advanced course. But just to give you some tip here, what we need to do is we simply put a message on the console saying an unexpected error occurred. Now, if we run this application, the application doesn't crash and we get a friendly error message. This is better in terms of the user experience. You don't want to write an application that crashes. No one likes that. Okay, I'm going to move all this code into a separate method. So static void use points. And I take everything here and pass it here. Okay, now let's go and create a calculator class. So public class calculator. We want to create a method called add that takes a varying number of arguments. So public int add. Here we add the params keyword, params, and then an integer array, and the name of the parameter is going to be numbers. Now inside this method, numbers is an integer array. So let's say we have an integer array and we want to add all the numbers in that array together and return the result. First, we create a variable called sum, set it to 0, and now we use a for each block to iterate over the numbers and simply add every number to the sum. And finally, we return sum. When you get to the advanced level, there is a better way to write this code, and that involves using LINQ or language integrated query. It's one of the powerful features of C#. Again, I have covered it in my C# advanced course. So for now, let's just keep the code the way it is. Now we put this class in a separate file. So Alt and enter and enter. Now we're back to the program. Let's create an instance of the calculator. Var calculator. Now we can call the add method, like passing two numbers, and we can simply display the result on the console. Or we can pass 3 parameters, or 4, or whatever. It's up to you. You can pass a varying number of parameters, and that's the effect of the params keyword. We can also call this method using an array notation. So let me paste that again here. Instead, I can pass a new integer array and put all numbers here. But as you see, it's easier to simply pass all the parameters without the need to create an integer array. And that's why we use the params keyword. Okay, let's put this code in a separate method and move to our third example. So I'm going to create another static method here. Use params. Let's move everything here. All right, the third example involves using the out modifier. I told you, do not use the out modifier when declaring your methods, but there are cases in the .NET framework where you may have to use the out modifier. So let's see an example of that. Let's say we have a string and we would like to convert it to a number. We can use the parse method of the integer class. So type int.parse and pass an invalid string here that cannot be converted to a number. Let's store the result in the number variable and run the application. Look, the application crashed. We got an exception, a format exception. Input string was not in a correct format. Okay, now let's take a look at the try-parse method. So int.try-parse. Look, it has 2 overloads. The first one takes a few parameters. The second one takes only 2 parameters. So I'm going to use the second one. It's easier. It takes a string, and that is the string we would like to convert. It takes an integer that is decorated with the out modifier, which will have the result of conversion if successful. And finally, it returns a bool, which indicates whether the conversion was successful or not. So let's pass the string here, ABC, and here we need to pass an integer. So int number. And because it's declared with the out modifier, we need to use the out keyword here. So number, and it returns a bool. So var result. So if conversion is successful, result will be true. And we can check that and display the number on the console. Otherwise, we can say conversion failed. Let's run the application. So look, we got a message called conversion failed. Now, how is it different from the parse method? The difference is try parse does not throw an exception. And that's the reason it returns a boolean to indicate whether the conversion was successful or not. The downside is that you have to declare this integer separately and then use the out modifier. Some people don't like the try parse method and they prefer to use parse, but then you have to handle exception using a try catch block, as we learned a little bit earlier. Something like this. So here we would say conversion failed. These two pieces of code are kind of equivalent. Now this number is actually declared somewhere else, so let me change it to just num. There you go. So here are two examples. I hope you enjoyed this lecture and thank you for watching. Okay, we got to fields. At the beginning of this section, I gave you a brief explanation of fields. A field is like a variable that we declare at the class level, and we use that to store data about the class. So in this lecture, I'm going to talk about a couple of different ways to initialize fields, and then I will talk about the concept of read-only fields. So in the last lecture, you saw me declaring a class called customer, which had a list of orders. And you also saw how I initialized that field using the default or the parameterless constructor. While this approach is perfectly fine, there is also another school of thought when it comes to initializing fields. Some developers believe we should use constructors only when we need to initialize our fields based on the values passed from the outside. So in this case, we are initializing the orders field without any external values. The constructor, as you see here, has no parameters. So in situations like that, there is another way to initialize the orders field. And that looks like the code you see here. So we can directly initialize the orders field without the need to create a constructor. This approach has an extra benefit, and that is we can have multiple constructors, and no matter which one is called, the orders field will always be initialized to an empty list. We'll explore that later when we start coding. Okay, now let's take a look at read-only fields. We can declare a field with the read-only modifier to make sure that that field is only assigned once. So in that case, that field has to be initialized either directly, like the slide you see here, or in one of the constructors of the class. You might wonder, why do we need something like that? The reason is to create some kind of safety in our application to improve robustness. For example, take a look at this customer class here. By declaring the orders field as read-only, I'll make sure that we'll only have one list where we will keep the list of orders. If I accidentally, as a developer, try to reinitialize this field in another method, the data that we had in the field will not be lost. It's easier to explain that using an example. So let's start coding and see these concepts in action. Okay, let's start by creating a customer class. So public class customer. Now let's declare a couple of fields. So public int ID, public string name. We can also create an order class, public class order. I'm going to leave the implementation of this class for now. We don't really need it for this example. All we need to do is to create a list of orders and the customer. So public list of order. Now let's declare a couple of constructors for this class. So setor. The first one may get just an ID. So this.id equals ID. The second one is going to get an ID and a name. And just to recap what we learned in the constructors lecture, we can use this keyword here. And instead of repeating the initialization of the ID, like the code you see here, we can delegate the control to this constructor here. So I'm just going to use this keyword, pass the ID. At this point, this constructor will be called. So the ID will be initialized based on what we get here. And then here, I can say this.name equals name. Now, if you remember from the lecture about constructors, I explained why we need to initialize these orders to an empty list. Just to recap, whenever you have a class like customer, and inside that class you have a list, you should always initialize that list to an empty list. Now, the technique I showed you in that lecture was to create a default constructor like the one here and set the orders to an empty list like here. This approach is perfectly fine, but there is a slight problem with that, and that is if we use any of these constructors here, so this one or this one, we have to make sure that the default constructor is always called first, so the orders field will be initialized. Some developers argue and say, no, we shouldn't initialize fields like the orders here, because orders is not dependent on any parameters from the outside. So what we can do is we can get rid of this constructor and initialize the orders field here. This way, no matter which constructor is going to be called, the orders field will always be initialized to an empty list. Some developers do not like this approach because they don't like the idea of initializing some of the fields here while declaring them versus initializing the others in the constructors. It's entirely up to you. It's more a personal taste. I wanted to show you both approaches so you know what is possible. The approach you choose is up to you, but what I want to emphasize to you is to be consistent with your approach. Make sure you use the same approach everywhere. This way your code would be cleaner. Okay, now let's move on and look at read-only modifier. So here, I want to declare a method. Let's call it promote, and the intention is this method will promote this customer to a gold customer. I'm going to leave the implementation here. Let's just put some comment. But I want to show you a mistake that I, as a developer, can accidentally make. Let's say if I accidentally reinitialize these orders here, what would happen? So what I'm going to do is, to clean up our code, I'm going to put this customer class in a separate file. So cursor here, I explained this earlier. So with resharper, Alt and Enter again. Now this class ended up in a separate file. So that file is customer.cs. Now we go back to program. We can do the same with the order class. Back to the program. Now the code is cleaner. Let's create a customer object. So var customer equals new customer. We're expected to supply an ID and or a name because we don't have a default or parameterless constructor. So look, here we've got two constructors. I'm going to use the first one. Doesn't really matter. I'm going to add two orders to this customer. So customer dot orders dot add new order, and let's just copy paste this line. So at this point, if I display the number of orders the customer has, we should see 2 on the console. So let's quickly do that. Customer.orders.count. Let's run the application. So we got 2 on the console. Now let me show you something. Imagine here, we make a call to the promote method. This method, because of a bug, accidentally reinitialized the orders field. So now if we run the application, all the data that we had in the orders field is lost. We have 0. This is where you use the read-only modifier. So let's go back to the customer. If there are situations where you know that this field should be initialized only once, that's where you decorate that with the read-only modifier. This way, if you accidentally reset that field in the code, you're going to get a compile time error. First of all, we can immediately see this error here by the red underline. It says read-only field cannot be used as an assignment target. So if you don't see the red error when you compile the application, you're definitely going to see that. So a read-only field cannot be assigned to except in a constructor or a variable initializer. So what this means is this line is not acceptable, and we can only initialize a read-only field either here directly when we are declaring that or in the constructor. So read-only is one of the ways that you can improve the robustness of your application. That's it for this lecture. I hope you enjoyed it, and thank you for watching. Okay, access modifiers. So far, you have seen me declaring classes and their members with the public keyword. Public is what we call an access modifier. In C# we have totally 5 access modifiers: public, private, protected, internal, and protected internal. In this lecture, I'm going to talk about public and private, and we leave the rest to when we get to the lecture about inheritance. So what is an access modifier? An access modifier is a way to control access to a class and or its members. Now you may wonder, why do we need to control access to a class or its members? The reason is to create some kind of safety or guard in our applications, to improve the robustness. In the lecture about fields, I explained how we can use the read-only modifier to make sure that a field is assigned only once, and this way we developers will not accidentally create bugs in our code. Take a look at this example. Here I've declared a customer class with a name field that is declared as private. With this code, when we declare an instance of the customer, we cannot access the name field. So we cannot go john.name. That will not compile. Now you may wonder, why do we need something like that? Well, that's the beginning of object-oriented programming. In object-oriented programming, which is actually one of my absolute favorite topics, we have 3 major concepts: encapsulation, which is also referred to as information hiding, inheritance, and polymorphism. In this lecture, we're going to learn about encapsulation. And throughout this course, we'll see more examples of achieving encapsulation. We're going to leave inheritance and polymorphism to the later section in this course. Let's start with encapsulation. I want to use an analogy. Think of a restaurant. In a restaurant, we have several roles. We have a cashier, we have a manager, we have a chef, we have 1 or more kitchen hands, we have 1 or more waiters or waitresses, and all these roles collaborate together to provide an amazing experience for you. Well, hopefully, because sometimes we go to a restaurant and we come back very disappointed. But anyway, think of the interaction between a waitress and a chef. A waitress takes the order and passes it to the kitchen. Then the chef looks at the order and does his job, and when it's ready, he notifies the waitress. So that chef is responsible for a few things, which is outside the responsibility of the waitress. A waitress is not going to go to the kitchen, tell the chef how to chop the vegetables and how to cook the meat and I don't know about different spices. Each of these roles are responsible for their own things. They have some knowledge and some capabilities. They perform some functions. Software should be the same. In software, we don't have a chef or a waitress, but we have classes. And these classes collaborate to perform the functionality required from the application. Now, we want to design our classes such that each class is responsible for one thing. It does only one job and does it perfectly. We want our classes to hide some of the information about how they do the things they are responsible for. We don't want other classes to know about the details of other classes. And this is what we call encapsulation. So we want to encapsulate some data in terms of fields, as well as some behavior or functionality in terms of methods in classes, and we want to hide the details from the outside. So when it comes to fields, we want to declare them as private and provide methods that would give access to these fields. We call these methods getters and setters. And these methods are going to be public. So we think of fields as the implementation detail, which should be invisible from the outside. It's how a class stores something in memory. We don't want any other classes to know anything about that. So to show you an example, here we have a person class that has a name field that is declared as private. So with this code, if we create an instance of the person class, we cannot access the name field of that object. Instead, we need to call one of the methods here, setName or getName. Look at the setName method here. The interesting thing about this method is that it does a check before assigning the name field of the person. So if the value that is passed to this method as the argument is null or empty, it's not going to set the name field. And that's one of the advantages of providing setters and getters. We cannot achieve the same thing with a field. A field is purely a storage in the memory. It doesn't have logic. With a setter or a getter, we can have some logic when accessing that field. Okay, before we start coding, I just need to emphasize something here. In terms of naming convention in C#, we have two naming conventions. One is called Pascal case, the other is called camel case. With Pascal case, the first letter of every word should be uppercase, like the person here, or name, or set name. Note that the first letter of every word is uppercase. With camel case, the first letter of only the first word is going to be lowercase, but the first letter of every word after that is going to be uppercase. An example of camel case is the name parameter here. So the first letter is lowercase. Now, when it comes to classes, we need to use the Pascal case when naming the class or any of its methods. For fields, the convention is to use the camel case prefix with an underline. So we need to change the name field here to something like this. So private fields should start with an underline and they should follow the camel case. Okay, I think that's enough theory. Let's start coding and see all these concepts in action. Okay, let's declare a class called person. And now we can declare a field called birthdate, which should be of type datetime. But we no longer are going to declare a field as public. Instead, we're going to use private. So private datetime birthdate. Note that I have used an underline here and camel case. So the first letter of the first word is lowercase. Now with this code, we cannot access the birthdate field outside the person class. So if we go to the main method here and create a person object, person dot, see, we don't see the birthdate field. It's hidden from the outside. And that's what we mean by information hiding in object-oriented programming. Okay, then how do we set a birth date? For that to happen, we need a method. So let me remove this for now. Back in the person class, I define two methods, public void set birth date, and this method takes a parameter of type datetime, and we call it birth date. At this point, if there are any logics around birth date, we can implement them here. In this case, we're going to keep things simple. We don't necessarily need the logic around birth date at this point. So what we need to do is simply set the birth date to the value passed to this method. And we declare another method, public datetime get birth date. And this method simply returns that birth date field. Now with these two methods, we can go back to the main method here and say person dot set birth date. We can say new date time 1982-1-1. And of course, we can read the birth date. So console.writeLine person.getBirthDate. We can run this application and we got the birth date on the console. Okay, I know what you're thinking. You probably are confused why we changed the access modifier for birth date to private, but then gave two methods here that directly modify the field or return this value. How is it different from directly going to that field? Well, if that's what you're thinking, it's in fact a good question. That's one of the questions I also had when I started with object-oriented programming. The answer is objects are about behavior, about what they do. Their fields is primarily their internals, their implementation detail, which should be hidden from the outside world. Even though in this example, it doesn't really make a difference whether we had a public field or a private field with two methods. But from an object-oriented perspective, we want to follow the principle of encapsulation, which suggests that objects should hide their implementation detail and reveal what they can do, as opposed to how they do what they're supposed to do. With the examples I will show you throughout this course, you will realize the importance of this concept more and more. Well, that's it for this lecture. What I want you to take away from this lecture is we're going to declare our fields as private, and the naming convention is underline and camel case. In the real-world applications, we are not going to define two methods like the ones you see here. This was purely for demonstration, and because I want to take things in a step-by-step fashion. In the next lecture, I will show you an easier way to achieve the same functionality, and that's what we call properties. I hope you enjoyed this lecture, and thank you for watching. In the last lecture, we talked about fields and encapsulation. You learned how to write a getter and a setter. In this lecture, we're going to continue that topic and see how properties can help us achieve the same thing with less code. So what is a property? A property is a class member that encapsulates a getter and a setter for accessing a field. So why do we need a property? Simply for creating a getter and a setter with less code. So let's see how we can write a property. Here is the code we wrote in the last lecture when we were working with fields. So to recap, we have a person class which has a birth date field, which is declared as private. And we have two methods here, setBirthDate and getBirthDate, which provide access to this field. As you can guess from this example, writing these two methods for every field is a little bit time consuming and tedious. Imagine if this class had 5 more fields. We would end up with 10 accessor methods, and that's not really efficient. So we can achieve the same thing with a property. If we want to convert this code to use a property instead of 2 accessor methods, this is how the code is going to look like. So we still have the birth date field, which is declared as private, and here we have the property. Note that the property is declared as public, and it should have the exact same data type as the field. In terms of naming convention, we use Pascal case for naming properties. So the first letter of every word should be uppercase. A good way to remember this is whenever you're working with classes, you should use Pascal case in most cases. So the class name, the properties, and the methods, they all use Pascal case. The only cases where we use camel case is private fields, as you see here, which should also be prefixed with an underline. And another case for camel case is the method parameters. Okay, let's move on and look at our property here. So inside this property, we have a get method and a set method. Note that the get and the set here are C# keywords, so they should be lowercase. And they have a code block, as you see with the curly braces here. Inside the get method, we simply return the field. And inside the set method, we use the value keyword to get what is on the right side of the assignment and copy that to the birth date field here. Note that in this case, we don't have any logic around the birth date field. So our get and set methods are pretty simple. We can write even less code to achieve the same thing. That's when we use auto-implemented properties. So here is how we can declare an auto-implemented property. So we have the property declared here, public, datetime, birth date, and there is no field. We just have a get, semicolon, and set, semicolon. When C# compiler sees that, internally it creates a private field for us. So we don't have to do that. Okay, I think that's enough theory. Let's start coding and see all these concepts in action. Okay, let's declare a person class first. So public class person. We want to represent the concept of birth date for this class. So I'm going to just go ahead and declare an auto-implemented property without declaring a field. So public datetime, birth date, we open the curly brace, get semicolon, and set semicolon. With this code, C# compiler internally creates a private field and implements the get and set accessor methods for us. Let me show you how it works. So I'm going to compile this application. To compile, we press Ctrl, Shift, and B. So build succeeded, as you see here. Now we go and right click on the project. Note that here I have an item called Open Command Prompt. If you don't have this in your Visual Studio, you need to install Visual Studio Productivity Power Tools. It's an extension to Visual Studio, which makes coding a little bit more pleasing and easier. So how you can find it is you go to Tools, Extensions, and Updates. You go to Online, and in the search box, type Productivity Power Tools. There you go. Know that I have installed this plugin, and that's why we have this green tick here. So in your case, you probably have to click it and then you select download. You probably have to restart Visual Studio. Then you will get this Open Command Prompt. And the benefit of that is it takes you directly to where the project is. Without this tool, what we need to do is to go to Start, Open Command Prompt, and use cd / whatever to find that directory where the project is located. Okay, now I want to show you the actual code that is generated by the C# compiler behind this auto-implemented property. So first, let's take a look here. dir, we've got a bin folder. We go to bin, dir, cd debug. This is where the compiled files or the assemblies are located. So take a look. Let me clean this up. So here we've got properties.exe. And the name of this project is called properties, and that's why we got this properties.exe here. It's an executable. It's a console application. Now what we need to do is we type ILDASM. That stands for IL disassembler. IL stands for intermediate language, and that's the target language that the C# compiler translates your C# code into. Any language that targets .NET Framework eventually translates its code to IL. In .NET Framework, we have a component called CLR, or Common Language Runtime. And what it does is, at runtime, it takes your IL code and translates that into the native or binary code for the machine on which it's running. So let's take a look at the IL code and see what it looks like. So with IL disassembler, we can here pass the name of the executable or the assembly, properties.exe. So here is IL deasm. Note that here is a namespace, properties. We expand that. We have two classes, person and program. Let's actually put this here. Okay, so here's our person class and here's the program class. I expand the person class. Note that here we have what is called a backing field. It's private and it's of type datetime. This is the private field that the compiler automatically created for us. And here we have two methods, get_birth_date and set_birth_date, which is similar to the code that you saw in the slides. And here is the property. If I double click that, note that it has a get pointer here, which simply calls the getBirthDate method. It also has a set pointer here, which calls the setBirthday method. Let's close this. Also note that here we have a constructor. And that's the default constructor that I told you the C# compiler creates for us. The job of this constructor is to initialize the class to an early state. So it sets all the fields of this class to their default values. All right, let's move on. We close this. I want to show you a few important things here. First, put the cursor here. Let's declare a property called age. So public int age. This property cannot be an auto-implemented property. Why? Because here we need some logic. I want this age to be based on the birth date of that person. So if I just type get and set here, internally the compiler would create a private field, and that age field will not be based on the birth date. Instead, what we're going to do is create a getAccessor method here, and here we're going to have some logic. So what we need to do is to get today's date, so datetime.today, and we subtract that from the birth date. When you subtract two datetime objects, you get a time span. So let's store the result in a time span. Note that if I hover my mouse here on the var, you see the data type of this object called timespan is timespan. And timespan represents a duration. So I can get timespan.days and divide that by 365, and that would give me the total number of years. And finally, I will return that. Before we move on, I would like to put this class in a separate file to clean up my code. So, cursor here, Alt and Enter, Enter. Now back to our program class. So let's create an instance of the person class, var person equals new person. We set the birth date, person.birthdate equals new datetime 1982-11. Now let's display the age on the console. Console.writeLine, person.age. We run the application. 33. Now let's get back to the person class. Note that here in the age property, I just declared a get method. I didn't declare a set method, and that was intentional because it doesn't make sense to set the age of a person. The age should be calculated based on the birth date. So with normal properties, like the age property here, if you don't want that property to be settable, you just don't declare a set method. But what about auto-implemented properties? Let's say we have this requirement in our application that the birth date of the person should be set once and it cannot be changed. So how can we achieve that? With that requirement, what we need to do is to go in this property and put a private accessor before the set method. With this, if I go back to the program, you see this red underline here. And the tooltip says the property birth date cannot be used in this context because the set accessor is inaccessible. So then how do we set the birth date? We have only one place, and that's the constructor. So we need to create a constructor for this person class where we get the birth date, and we set this property, and that's it. The property can no longer be changed. So let's declare a constructor, ctor tab. Here we get a datetime parameter, datetime, call it birth date, and we set the birth date property. That's it. Back to the program. We need to modify this code because now we have a constructor that takes a parameter. So I'm gonna select this code and put that here, and then get rid of the birth date. So let's review this again in our person class. We have two properties here. One is an auto-implemented property, which doesn't have a back-in field. This property has a private set accessor, which means it's read-only. You cannot change it. And we set that in the constructor here. We also have another property which doesn't have a set method either. This property calculates the age based on the value of another property. What I want to emphasize in this lecture is you should make sure that your classes are always in a valid state. That's the key. Your classes should never lie. They should never be in a false state. In the example here, I have implemented this concept using a private accessor here, and by removing the setAccessor in the age property. So this person class, this person object is always in a valid state. We set its birth date, it cannot be changed, and the age is calculated based on the birth date. Okay, before we finish this lecture, I want to show you two more things. First, I want to show you a quick way to declare properties. And next, I want to tell you about the convention we should follow in C# when working with classes and their properties. So let's say we want to declare an auto-implemented property called name for this person class. So what I'm going to do is, I go here on the top. Instead of typing public string name, curly brace, get set, I'm going to do a shortcut. So let's get rid of this. I just type prop, as in short for property, and press tab. That's a code snippet. Now note that the type is highlighted. So here I type in string, I press tab. Again, now the identifier is highlighted, and I give it a name. And finally I press enter. That's it. This is much faster. Let me do this one more time without explaining it. Isn't it faster than typing the whole thing? So that's one thing. Now, another thing is in terms of convention, you might be wondering, where should we declare our properties? On the top, on the bottom, in the middle? Well, actually, I made a mistake here. This birthdate property should be on the top. So what we need to do is we put all our properties on the top. Then we have the constructor. And note that there is a vertical space between all these properties and the constructor. If the code was like this, it would look a little bit squashed. It looked dirty and ugly. So always declare all your auto-implemented properties on the top, have a vertical separator, and then put the calculated properties on the bottom. Well, that's it for this lecture. I hope you enjoyed it, and thank you for watching. Okay, we got to indexers. What is an indexer? Indexer is a way to access elements in a class that represents a list of values. What do I mean by that? Well, let's take a look at a few examples. You have already worked with indexers. Here are a couple of examples. So here we have an array of integers, and this is an indexer. So you can access the first element of an array like this. Or here is a list of integers. And again here, using an indexer, we can access the first element in this list. Now you might say, we already have the concept of lists and arrays and collections, so we are not going to reinvent the wheel. Why do we need to define an indexer in our class? Well, sometimes we have classes that have collection semantics. For example, think of an HTTP cookie. An HTTP cookie, in case you're not familiar with that, is a file that is sent from your browser to the web server upon each request. We web developers use a cookie to identify a user. We can store some settings about the user in that cookie. In that cookie, we have a list of names and values. So imagine in a project we have implemented the concept of HTTP cookie. Now the code that consumes our HTTP cookie class might look something like this. So here we are creating an instance of the HTTP cookie class. We set the expiry date, and here is where we can use an indexer. So with this indexer, I'm specifying that the name of the user is Mosh. Without an indexer, we have to write a method like setItem here and pass a key and a value. You see that achieving the same thing with an indexer is easier and requires less code. If you want to get the value of a cookie item using an indexer, here is what the code would look like. So we simply use the indexer, pass the key, and we get the value. Without an indexer, we have to write a method like getItem. Again, the code that uses indexer is easier and shorter. Now, in real-world projects, it's unlikely that you're going to create an HTTP cookie class because it's already part of .NET Framework. But I use this as an example in case you're working with a class that has the semantic of a list or a collection or a dictionary. That's where you can improve your code by using an indexer. It's not something that you may see every day in your career, but I want you to be aware of this feature. Now, how can we declare an indexer? An indexer is nothing but a property. So we can declare an indexer exactly like how we declare a property. So we have the data type, like string. Then instead of an identifier, we use the this keyword. And here's the indexer notation. So brackets. And inside the bracket, we have the type of indexer. So in this case, with the HTTP cookie, I want to find items by their key, which should be a string. So my indexer here is a string, and I give it the name of key. The rest is exactly like declaring a property. We have a get method and a set method. And here we write the logic for accessing the particular element. Let's start coding and see this in action. Okay, we first start by creating an HTTP cookie class. HTTP cookie. Now I'm going to put this in a separate file. You have already learned that before. Alt and enter. Okay, now we need a field to store the key value pairs in the cookie. The data type or the data structure we use for that is a dictionary. If you're not familiar with a dictionary, it's a data type that resides in system.collections.generic, and it uses a hash table to store data. A hash table has a special mechanism that makes it extremely fast to look up an item by its key. So whenever you have a list of objects and you want to look them up by a key as opposed to an index, you should use a dictionary. If you have a list of objects and you would like to look them up by an index, then a list is a better choice. Okay, now let me declare a dictionary, private dictionary. I want this dictionary to be of type string and string. Now, what this means is this is a generic class. This is a generic class, and these are generic parameters. And these parameters specify the type of the dictionary. So in this case, I'm specifying that the keys should be of type string and their values should be also of type string. Okay, now let's give it a name. Dictionary. I would like to initialize this in the constructor. Dictionary equals new dictionary. That's it. Just want to recap what we learned earlier. We could potentially go and initialize this field straight here. And that's perfectly fine. It's entirely up to you. You can do it here or in the constructor. Now back here. Okay, now we need an indexer. Declaring an indexer is exactly like a property. So what we're going to do is public. The return type is string because we have key value pairs and they both are string. So string. Now an indexer doesn't have a name. We use the this keyword. So this, and here's the indexer notation. We use string to represent the keys for our key value pairs. So string key, and here inside this property, we have a get and a set method. Now, the implementation is very easy. All we're going to do is to delegate to that dictionary. So for get, we're going to return dictionary of key. So internally, we rely on the dictionary to store the key value pairs. And HTTP cookie is simply a wrapper around that. Now let's implement the set method. Again, very similarly, dictionary of key equals value. And this value is a keyword which represents what is on the right side of the assignment operator. Note this green underline here. That's ReSharper's highlighting feature. So if there are areas in the code that can be improved, ReSharper highlights them with a green underline. In this case, it's saying field can be made read-only. And this is a great example of using read-only because we don't want to accidentally reinitialize that dictionary and lose all the data we stored in it. So here I can just press Alt and Enter and let ReSharper apply the read-only modifier for me. There you go. So as you see with ReSharper, you tend to code less and you can delegate a lot of things to ReSharper. Okay, now this is ready. We can go back to our program. Let's create an instance of our HTTP cookie. Var cookie equals new HTTP cookie. We can store a key value pair using the indexer. So cookie of name equals mosh. So name is the key and mosh is the value. And we can read that from the cookie. So console.writeLine cookie of name. Let's run the application. So the cookie is working. Now let's get back to HTTP cookie class. You might be wondering, why did we create an HTTP cookie as a wrapper around the dictionary? Couldn't we just go ahead and use the dictionary directly? Well, yes and no. In this case, in this simple example, yes, we could definitely just use a dictionary as an HTTP cookie. But an HTTP cookie is more than a dictionary. For example, it can have a property called expiry, and that's the expiry date time for the cookie. So we can go here and create an auto-implemented property for that. So prop, remember that? Tab, that's a code snippet. Date time. Expiry. Our cookie can have other properties or methods. And now it's more than just a dictionary. Internally, it uses a dictionary for data storage. So the takeaway from this lesson is, if you're working with a class that has the semantic of a collection or a list or a dictionary, you can improve your code by declaring an indexer. An indexer is an easier way to access elements in that collection, as opposed to having two methods. Like here, if we didn't have this indexer, we had to create a method like public void setItem string key string value. And we also had to create another method like public string getItem string key. There's nothing wrong with this approach, but it's more efficient to just use an indexer, both in terms of the code in the class here, as well as the code that we wrote in the consumer here. Okay, that's it for this lecture. I hope you enjoyed it, and thank you for watching. Okay, in the last section, you learned about classes. In this section, we're going to talk about class coupling. What is coupling? In software engineering, coupling is a measure of how interconnected classes and subsystems are. At the beginning of this course, I explained that a software application is composed of many classes that are packaged inside various namespaces and assemblies. In this picture, we have the classes inside an application. Assume that we need to make a change in class A. Now, class B and class F are both dependent on class A, which means if A changes, B and F may have to be changed, or at least they need to be recompiled and redeployed. So the change in A may affect B and F as you see here. But also, class D and class C are dependent on class B. Similarly, class G is dependent on class F, which means changing class A has a bigger impact on our application. And again, you see here, class E is dependent on class D, and class H is dependent on class G. So changing class A affects even more of the application. This is an example of tightly coupled design. So an application whose classes are tightly related or dependent on each other is considered to be tightly coupled application. And this is very bad, because there is a chance that we may break things along the way as a result of all these changes in the application. In contrast to tight coupling, we have loose coupling. So in this picture, I'm demonstrating the concept of loose coupling between classes using a dotted arrow. And this is the ideal software. We want to minimize changes in our application. So when we change a class, we want that change to be isolated. We don't want that change to affect other parts of the application. Now you might ask, but how do we design a loosely coupled application? Well, there are three things you need to understand. The first one is encapsulation, which I explored in the last section. Remember I talked about the restaurant? In a restaurant, we have various concepts, like a manager, like a cashier, a waiter, waitress, a chef, kitchen hands. A waitress does not go to the kitchen and tell the chef how he should chop the vegetables and how he should cook. That's the responsibility of the chef. So the chef has some knowledge and some capabilities. And if you want to model the concept of chef in software, we want to encapsulate all those concepts in a class. So no class from anywhere else in the application knows about details of how things are done in that class. And you saw how we could use access modifiers to achieve that. Now the next thing you need to understand is the relationship between classes, which is the topic of this section. And finally, you need to understand interfaces. Interfaces are extremely important, and they help you design loosely coupled applications. That's why I have dedicated a separate section to interfaces. So let's start with the relationships. In general, we have two types of relationships between classes. We have inheritance and composition. So over the next couple of lectures, I'm going to talk about inheritance and composition, both in terms of theory and practice. And finally, I will talk about the concept of favor composition over inheritance. Composition relationships usually result in less coupling. And that's the meaning of this concept, to favor composition over inheritance. So let's get started. Okay, inheritance. In this lecture, I'm going to tell you what is inheritance and why we use it. Then I'm going to show you an example of inheritance using UML notation. UML stands for Unified Modeling Language, and it's a graphical language for representing classes and their collaboration. And finally, I will show you the syntax of inheritance in C#, and then we'll do some coding. So let's get started. What is inheritance? Inheritance is simply a kind of relationship between two classes that allows one to inherit code from the other. It's usually referred to as is-a relationship. For example, we can say a car is a vehicle. With inheritance, we get code reuse. That means we encapsulate some common code in one class and then we reuse that in other classes. Inheritance also provides polymorphic behavior, which is extremely powerful. But it's beyond the scope of this section. There is a separate section in this course called Polymorphism, and that's where you will learn about polymorphic behavior. For this section, let's just see how we can use inheritance to get code reuse. Imagine we want to design an application like PowerPoint. Here I'm using Keynote on Mac, which is similar to PowerPoint on Windows. So on this slide, we can have objects like a shape, text, a table, and an image. All these objects have some common attributes. For example, they have a width, a height, and a position. They also have some common behavior. For example, if I right-click on this shape here, you see bring to front, send to back, cut, copy, duplicate, and so on. If our job is to develop an application like PowerPoint or Keynote, we can create classes for each of these objects. For example, we can have a class called shape, we can have a class called text, a class called table, and a class called image. Now, we don't want to duplicate all these common behavior and attributes in all these classes. So that's where we can use inheritance to write code once and reuse it in multiple contexts. Here is the UML representation of the candidate classes for our PowerPoint application. So at a high level, we can have a presentation object class, which is where we encapsulate those common behavior and attributes. Then we can have classes like text, table, and image, which inherit from presentation object. In this example, we refer to presentation object as a parent or a base class. Some people also refer to it as a superclass. Text, table, and image are referred to as child, derived, or subclasses. In terms of syntax, here is how we implement inheritance in C#. So here we simply create our common class, which is presentation object, and then we create a new class like text that inherits from that. We implement inheritance by simply appending a colon and the name of the base class after declaration of the child class. Okay, now let's start coding and see this concept in action. Okay, let's start by creating a class called presentation object. This class is going to be the parent or base of other classes. So public class presentation object. And here we can define a couple of properties like width and height. And a couple of methods like copy and duplicate. I'm going to leave the implementation very easy. So we just simply output a message on the console. So console.writeLine object copied to clipboard. Object was duplicated. Now let's put this class in a separate file. So back here with ReSharper, Alt and Enter, done. Now back to our program.cs. Let's create a new class that derives from presentation object. For example, text. Presentation object. So this is the inheritance notation. We just put a colon here and the name of the base class. Note that in C#, a class can have only one parent. Now let's define a few properties or methods that are specific to the text class. So, for example, font size or font name, and maybe a method to add a hyperlink to a text. Void add hyperlink. String URL. Now you may argue that we may need this feature on every presentation object, and that's perfectly valid. But for the sake of this example, let's just add this method here because I want to demonstrate the difference between a parent and a child class. So simply console.writeLine, we added a link to plus URL. Okay, to clean up our code, we go here and put this in a separate file. Okay, let's go back to our program.cs. Here, I would like to create an object of type text. So var text equals new text. Now we type text dot. Okay, here, as you see, we have members that are defined in the text class itself, like add hyperlink, font name, font size. But we also have members that we inherited from the parent class, which is presentation object. That includes copy method, duplicate method, height, and width properties. We also have a few methods that we define in neither the presentation object nor the text class. That includes the equals method here, or get hashcode, or get type, or toString. These methods are defined in the object class, which is the parent of all classes in .NET. So when you create a class, even if you don't specify the object class as its parent, it automatically inherits the members defined in the object class. I'll cover the object class in more details when we get to the section about inheritance. But what I want you to take away from this lecture is that we added some common functionality in the presentation object class that includes a couple of properties like width and height, and two methods like copy and duplicate. And we inherited all this code in the text class using inheritance. Now let's go back to program.cs and finish up this task. So text.width equals 100, text.copy. Let's run the application. So we got the message object copied to clipboard, and the implementation of that was in the parent class. Again, I'll cover inheritance in more details in the section called inheritance. For this section, all I want you to take away is that inheritance is a kind of relationship or association between classes, and it has two benefits. One is code reuse, another one is polymorphic behavior, which we'll learn about soon. I hope you enjoyed this lecture, and thank you for watching. Okay, we got to composition. In this lecture, I'm going to talk about what is composition and what are its benefits. Then I will show you how to represent composition using UML notation. And finally, I will show you how to achieve that in code. So composition, just like inheritance, is another kind of relationship between two classes that allows one to contain the other. We refer to composition as has a relationship. For example, we can say car has an engine. Just like inheritance, with composition, we get code reuse. But composition is more flexible, and it's a means to designing loosely coupled applications, as we will learn later in this section. As an example, imagine we are designing an application, and as part of that, we need to have a class called dbMigrator that is responsible for migrating our database. This class will be responsible for creating new tables, populating them with data, maybe renaming columns, dropping columns, and stuff like that. As part of that, it requires some logging. Perhaps we need to log each step in the text file. Also, in our application somewhere else, we could have another class called installer, which is going to be responsible for installing our application in a target environment. Just like dbMigrator, our installer also requires logging. So as you see, logging is something that is common between these two classes. What we can do in this case is to create a class called logger that is responsible for logging information to a text file. Here is a UML representation of this concept. So here, the logger class has the capability to log messages in a text file. dbMigrator and installer, they both have a relationship or association to the logger class. The type of relationship is composition, as indicated by black diamond on the left side of the relationship. In C# terms, composition is nothing new. So if you want to implement what you saw in the previous diagram, we simply create an installer class which has a private field called logger. In the constructor of the installer class, we get a logger object which we use to initialize that private field. So for composition, we don't have any special syntax like inheritance. The related class is simply a private field in the composite class. Now let's jump into code and see these concepts in action. Okay, we start by creating our logger class, which is where we have the common functionality. So I'm going to keep this class as simple as possible because what we want to learn in this section is about relationship or association between classes. We don't want to get distracted by details such as how to open a file, how to close it, how to write information to a file. So let's just leave that for now. So I'm just going to create a method called log that takes a message and simply writes that to the console. Now let's put this class in a separate file. So Alt and Enter, back with Control and minus. We create a new class called dbMigrator. This class is going to be responsible for migrating our database. So we create a constructor, ctor tab, there you go. Now here we need a parameter of type logger. We want to create an association to the logger class. So logger. And now with ReSharper, I can put the cursor on this parameter here and simply press Alt and Enter. And look, the first item is introduce and initialize field logger. So enter, it automatically created a private read-only field, as you see here, and initialized it using the argument passed in the constructor. Now let's say this class has a method like migrate. Public void migrate. And as part of migrating, which is going to be a complex task, we need to do some logging. So all we need to do is to call the log method of the logger class. So logger.log, we are migrating, blah, blah, blah. Now we put this in a separate file. We get back to program.cs using Control and minus. Let's create another class called installer. And we do the same technique there. So we create a constructor, ctor tab, create a parameter here, logger, Alt and enter again. There you go. We got the private field and create a method here called install. Again, as part of installing the application, we're going to log messages to our log file. So we simply call the log method of the logger class. So we are installing the application. Now let's put this in a separate file to clean up our code. Back to program.cs. Okay, now we create a dbMigrator. For dbMigrator equals new dbMigrator. Here we need to pass a logger object. So one way to do it is just to create a logger object here, like new logger. Another way is to declare a variable and assign it to the new logger. And then we can pass that variable to the dbMigrator's constructor. Let me show you this technique when creating a new installer. So var logger equals new logger. Now let's create an installer. Var installer equals new installer. So here again, we need to pass a logger object. So I'm just going to pass this logger object here. Now let's call dbMigrator.migrate. and installer.install. We run the application. So here are the messages that are supposed to appear in our log. So the interesting thing here is we declared that common functionality, which was about logging, in a separate class here, and then we reused that in two other classes using composition. So as you have seen so far, we have two ways to reuse code. One is inheritance and one is composition. They both are valid approaches, but which one you use depends on the project you are working on and its requirements. Generally speaking, inheritance results in a more tightly coupled relationship. With composition, we can get loose coupling plus more flexibility. And that's the reason a lot of developers say favor composition over inheritance. In the next lecture, I will cover this concept in more details. I hope you enjoyed this lecture and thank you for watching. In the last couple of lectures, you learned about inheritance and composition. In this lecture, I'm going to talk about problems with inheritance, and then I will explain the advantages of composition over inheritance. Before we start, let's review what you learned in the last couple of lectures. So you saw that with inheritance, we can get code reuse. I showed you an example of a presentation object where we wrote some common code that was inherited by text, table, and image classes. You also saw an example of code reuse using composition. So we had a logger class where we defined the logging capability, and then we used that class in DB migrator and installer. Now the problem with inheritance is that it can easily be abused by amateur designers and developers, which can easily lead to large hierarchy of classes. Such hierarchies are fragile. If you change a class on top of the hierarchy, all the classes inherited from that will be affected. And this is because of the tight coupling that comes with inheritance. Let me show you an example so you can see all these problems in practice. Imagine we are designing a game and we would like to introduce the concept of a person and a dog. Both person and dog classes can have attributes such as age, and they can have methods such as eat and sleep. So with inheritance, we can create an animal class and then derive person and dog from the animal. Now let's say we need to give the person and dog the capability to walk. So we need to go in our animal class and change that class by adding a new method called walk. The problem at this stage is because both person and dog derive from animal, they will be affected as a result of this change. Sometimes when we change a class, the dependent class may have to be changed, or at least it has to be recompiled and redeployed. Okay, now to make the matter worse, let's imagine we would like to introduce the concept of goldfish. So we add a new class called goldfish that derives from animal. But there is a problem here. The problem is that the goldfish cannot walk. So our inheritance hierarchy needs to be modified, which means we have to take that walk method outside the animal class and probably create another subclass called mammal, where it has the capability to walk, and then we can derive person and dog from mammal. So as you see, the hierarchy is getting changed again. So that's the reason inheritance can easily be abused by amateur designers and developers, and it results in large hierarchies. And such hierarchies are fragile because of the tight coupling between classes. Now I want to show you something. I want to show you that any inheritance relationship can be translated to a composition, and that can result in great flexibility. So let's review the same problem and see how we can model these classes using composition. So this time, instead of person and dog deriving from animal, they have an animal. Now the first thing that may confuse you here is that a person conceptually is an animal. At least that's how we define the concept of person in the English language. Well, that's exactly where the problem happens with inheritance. Most amateur designers try to model software using real world. Just because in the real world a person is an animal doesn't mean we should always use the inheritance or is a relationship between these two classes. We as software engineers need to think differently. We need to design our classes such that a change in a class is isolated and has minimal impact on other classes in the system. And doing so requires a different way of thinking. not the way that we think in the real world. We basically need to think in objects. Okay, back to our example. Let's say we forgot to give the person and dog the ability to walk. Now, how can we model that using composition? Well, first we introduce a new class called walkable, which has a method called walk. This walkable class describes the behavior of walking for any kind of animal. Next, we create a composition between person and walkable. Same for the dog. Now, what happens here is that a person has an animal and it also has a walkable. So it has the capabilities defined in both animal and walkable. Now, let's say we would like to add a goldfish. So we create a new class called goldfish that is composed of animal. Goldfish cannot walk, so we are not going to create an association or relationship between goldfish and walkable. Note that in the example with inheritance, adding the goldfish class broke the hierarchy. But here we simply added a new goldfish and created a composition between goldfish and animal. Person is not modified, dog is not modified, animal is not modified, neither is walkable. Now let's say we would like to give our goldfish the ability to swim. So we can create a new class called swimmable, which has a method called swim. And then we create a composition association between goldfish and swimmable. Again, none of the classes in the system have been modified. Tomorrow we can introduce a new class called duck. A duck is an animal, it can walk and it can swim. So again, we can create a composition between duck, animal, walkable and swimmable without any impact on person, dog and goldfish. So as you see, with composition, we encapsulate some common functionality and then we compose them together, we tie them together to create new classes. Using this technique, we can create new classes with new capabilities of the existing classes. We compose them together. And this has minimal or zero impact on other classes. So with composition, we get great flexibility, but we also get loose coupling. How? Let's take a look at both the composition and inheritance relationships in terms of coupling. So here in this picture, we have both an example of inheritance and composition. In this example, coupling between person and animal, irrespective of the kind of relationship, is equal. So whether we use inheritance or composition, if animal is changed, person may have to be changed or at least needs to be recompiled and redeployed. But there is a catch here. With composition, we get an extra benefit, which is not possible with inheritance. And that is, we can replace the animal class on the right side with an interface. Interfaces are extremely powerful, and that's the reason I've dedicated a full section on them. For this lecture, don't worry about it. All I want you to take away from this lecture is that we have two types of relationships between classes. One is inheritance, which is also referred to as is-a relationship, and another one is composition, which is referred to as has-a relationship. Both inheritance and composition have pros and cons. Inheritance provides code reuse, and it's easier to understand than composition in certain examples. For instance, in the example you saw earlier, we usually think a person is an animal. So modeling that using composition like person has an animal is a little bit harder to understand. But the bad thing about inheritance is that it creates tight coupling. It can easily be abused and result in large hierarchies, which are fragile. A simple change can propagate to many parts of the application, and that change can be very costly. Composition, on the other side, provides great flexibility and loose coupling, but it's a little bit harder to understand in some cases. Now, I'm not telling you that inheritance is necessarily a bad thing. In fact, both inheritance and composition are great techniques, but you need to use them appropriately. What I want you to take from this lecture is just because in the real world we think of a lot of relationships as inheritance or is-a relationship doesn't mean we need to model them the same way in software. Because again, doing so can easily result in large hierarchies with many levels of inheritance. That's it for this lecture. I hope you enjoyed it and thank you for watching. Okay, we got to access modifiers. Earlier in this course, you learned about access modifiers. You learned about public and private. In this lecture, I'm going to explain access modifiers in more detail. I'm going to talk about why access modifiers are important. And to explain that, I'm going to use the black box metaphor. And finally, we get into C# access modifiers. So let's get started. A metaphor often used in object-oriented programming is black box. Look at this black box image here. We don't know what's inside this box. There is limited visibility. And there is just one, I don't know if it's a button or a light, and that's all we can see. We want to design our objects to look like a black box. So there is limited visibility from the outside, but there could be a lot of magic going on inside. Now you might wonder, why do we want to design our classes like a black box? It all comes back to isolating changes. The more a class reveals about its internals or its implementation, the more risky it becomes when we are going to change that class, because there could be other parts of the system that rely on that implementation. So we want to limit the visibility from the outside and make our class look like a black box. Here's another metaphor. Look at this DVD player. All we see from the outside is just a few buttons and an indicator. But there's a lot of complexity inside that DVD player. There's an electronic board with a lot of ICs, and who knows, there's a lot of complexity there. What we see from the outside is called public interface. Again, we want to design our class to look like this DVD player. So its public interface should be very simple. Now, in C# we use access modifiers to control visibility to members of a class. You have already seen public and private. But we also have protected internal and protected internal. Let's explore these access modifiers in detail. A member that is declared with public is accessible from everywhere. So in this example, we have a customer class with a promote method that is declared as public. With that, we can create a customer object somewhere else in the code and call the promote method. The promote method is going to be visible to the outside. That's perfectly fine, because promote should be part of public interface of the customer class. It's not about implementation. We may want to promote a customer, and that's an expected functionality. Now, private is the complete opposite of public. So a member that is declared as private is only accessible from that class. In this example, in our customer object, I have a method called calculate rating. We're going to use this method as part of promoting. So perhaps we need to do some calculation, and based on the result of that, we may promote a customer to a certain level. This is about implementation detail. It's about the internals of the customer class, how we promote a customer. We don't want other classes to know anything about that. So that's an example where we can use the private modifier to limit access to this method. So as you see in the example, if we create a customer object, we are not going to be able to call the calculate rating method. It's not going to be compiled. Okay, next is protected. A member declared as protected is accessible only from the class and its derived classes. What does it mean? Well, look at our calculate rating method again here. This time I declared it as protected instead of private. So this statement says accessible only from the class and its derived classes, which means outside this class, if you have a customer object, we are not going to be able to call this method. So it's a little bit similar to private. The difference is if we derive a class from customer, let's call it gold customer. That method is going to be visible in a derived class. Now, there is a problem here. The problem is, as we explained in the last slide, calculate rating is about the implementation detail, which should be encapsulated inside the customer class itself. We don't want anywhere else in the code we know about this method, because we may change it in the future. We may rename it, we may change its parameters, or we may even remove it. We don't want anywhere else in the code base any dependency to this method. Now, the problem with the protected modifier is any classes derived from this class will still be able to see this method. And that breaks encapsulation, because as I've explained throughout this course, encapsulation is about hiding the details inside a class and only revealing the minimal. That is the public interface of a class. So a lot of developers consider protected a bad design in the C# language. Having said that, you will see a lot of places in the .NET framework or in many other libraries where protected is used. Now, to make all this easier for you, what I'm suggesting is avoid it if you can and prefer to use private methods. But if there are circumstances that you have to use protected and you have a valid reason for that, that's okay, go ahead and use it. Just be aware that you're revealing the implementation detail of a class to any of its subclasses, which can be trouble in the future. Okay, next one is internal. Internal is a modifier that we often use with the classes, not their members. It really doesn't make sense to declare a class member as internal. But there are cases that you may declare a class as internal. For example, continuing from our last example, imagine we have a separate class called rate calculator. And rate calculator might have a bunch of methods and some complex logic to calculate the rate for a customer. Now, this class is part of the implementation detail for the domain of customers. So, inside that domain, it's okay for every other class to see this class. But outside that domain, we don't want anyone else to know about the existence of this class. So how we implement that in C# terms is we create a separate class library, and in that class library, we declare the rate calculator class as internal. So inside that assembly or that class library, everywhere we will see this class. But outside that assembly, no one knows about this class. Again, I'm going to show you all of this stuff in the code. So if that sounds unfamiliar, don't worry about it. And finally, we've got protected internal, which I would say is the most weird thing in C# language. Basically, what it means is a member declared as protected internal is accessible only from the same assembly, and that's because of the internal, or any derived classes, and that's the result of protected. So here is an example. We have a customer class, and it has a method called weirdo that is declared as protected internal. Now, this is really bad, both in terms of teaching, learning, writing code, and someone reading that code. It takes a lot of brain power to understand what's going on. I just added that in this lecture because I want my course to be comprehensive, but it's very unlikely that you're ever going to need it. Okay, let's start coding and see all these access modifiers in action. Okay, let's start by creating a customer class. So public class customer. We can define a couple of properties like ID and name and a method like promote. Now let's go to the main method and create a new instance of customer. So var customer equals new customer. Now if we type customer dot, here is the public interface of this customer class. So we have a few methods like equals, get hashcode, get type, and toString, which are derived from the base object class. And we also have these bold members here that are defined in the customer class itself. So ID and name properties and the promote method. All of this together make up the public interface of the customer class. Now back to the black box metaphor or the DVD player, we want to minimize this public interface. The more we reveal about a class and its members, the more we risk that other parts of the code will be dependent on those members. So this creates more coupling, which means if we are going to change the implementation of our customer class, other parts of the code may get broken. Let me show you how this happens. So I'm just going to remove this. Let's create another method. We're going to calculate the rating of a customer. So just public int calculate rating. I'm going to leave out the implementation of business logic here and just return a simple number because we don't want to get distracted with some business rules and whatnot. What I want to show you is in the promote method, perhaps there is a call to this calculate rating. So we can say var rating equals calculate rating. And then based on what is returned from that method, we can make decisions. For example, if rating is whatever, then console.writeLine promoted to level 1, otherwise promoted to level 2. Just keeping it simple. Now the problem here is this method is about implementation detail of the customer class. from the outside, we don't really need to see this method. What the consumers of this customer class need to see is just this couple of properties here and the promote method. How the promote method does its job, which in this case means calling the calculate rating, is no one's business. So this is what encapsulation means. We're just going to hide the details inside and reveal the public interface. Now the problem happens if somewhere else in the code, we, out of interest or curiosity, have a call to calculate rating method. Now, because this is the implementation detail of the customer class, tomorrow we may decide to change it. For example, we may decide to pass a parameter like a switch, say, exclude orders. It might have some meaning in the business domain we are working on. So we're changing this method, and what happens is, see, we get this red underline here. Now, if this method is being used outside this class, like in this case in our main method, here the code is going to break. And imagine if there were 10 other places in the code where we made a call to this method. But in this case, if this method was declared as private in the first place, nowhere else we had a call to this method. And fixing that change would be as simple as just making a change in one place in the code, which is the promote method that is using this calculate rating method. So here I would say exclude orders true. But this is the reason we want to minimize the public interface of a class to the outside world. Now let's get rid of this calculate rating method here. Okay, now let's put this customer class in a separate file to clean up our code. So Alt and enter, enter. Now back to program. Let's create a class that derives from the customer class. So maybe call it gold customer. And add the customer here. Okay, here we can have a method like offer voucher. So let's say we're going to give a voucher to our gold customers. So public void offer voucher. And of course, this method needs some argument like a voucher object. But again, to keep things simple, let's not worry about the parameter. What I want to show you is inside this method, if we use this dot, see, these are the members that we see in this class. So equals, get hashcode, get type, member-wise clone, and toString were derived from the base object class. That is the parent of every class in .NET. ID, name, and promote are derived from the customer class itself. An offer voucher, which is indicated by bold, is declared in this class itself. So as you see, calculate rating method is not visible here because we declared it as private. So back to customer class. Look, calculate rating is declared as private. And my rationale was because this is the implementation detail, we want to encapsulate it. We don't want anywhere else in the code to have dependency to this method. Now, if we change this to protected and go back to our gold customer class, look, this dot, and here we see the calculate rating method. And here's the problem. We created a dependency to the implementation detail of the customer class. So again, if tomorrow we are going to change that method, maybe we rename it, maybe we add a parameter, or maybe we even delete that method, gold customer class is going to be affected. Let me show you this in action. So imagine as part of offering voucher, we're going to call this method and let's pass whatever switch here. And we get a rating here. And based on that rating, we're going to do some logic. Now, if tomorrow we go to the customer class and decide to totally drop this method, maybe our business logic for promoting a customer is changed. So I'm just going to remove this method. And let's say I'm going to change the logic of promote method, promote logic changed. Now see what happens in the gold customer class. So the calculate rating method does not exist anymore because we deleted it from the parent. Again, here is where encapsulation is broken. So try to avoid protected unless you have a valid reason to use it. For example, if you know that the concept of calculate rating is completely stable in the business domain you have been working on, maybe it's okay to use that. Also, as I said, there are some design patterns that use protected methods as part of their implementation. Okay, let's move on and see the internal modifier. So I'm going to just remove this class. Okay, to see the internal in action, we need to move our customer class to a separate assembly. So what I'm going to do is right-click on the solution, go to add. Actually, you're not going to see that in the screencast, so I just drag and drop the solution explorer to the left. So you can see, right-click on the solution, add, new project, and we select class library. So with a class library, we create a DLL, or dynamically linked library. And we can reference that in various applications. So give it a name. Let's say we are building an application for Amazon. So I'm going to call this class library Amazon. Now by default, we have class 1 in this project, this class library. I'm going to remove that. And then I move this customer class inside the Amazon class library. Yes. When we open it, note that here we have the old namespace. So we need to change that because now the customer class is inside the Amazon project. So with ReSharper, this is pretty easy. You just put the cursor here and Alt and Enter. The first item says move declarations to namespace Amazon. Enter. Done. So here in this project, we're going to implement all our business logic. We have the customer class, and we're also going to create a new class for calculating rating of a customer. So public class rate calculator, and it could have a bunch of methods and properties and fields. I'm just going to keep it simple. So let's have a method called calculate, which gets a customer object. And for simplicity, let's just return 0. In the promote method of our customer, I'm going to make a call to this calculator. So var calculator equals new calculator, new rate calculator, and rating equals calculator.calculate. And I pass this as the object, as the customer object to that method. And based on that rating, we can do some conditional statements and decide how to promote the customer. I need to add a caveat here. Generally speaking, it's not a good practice to instantiate a new object like the rate calculator inside a method here, because this creates coupling or dependency to this object. When we get to the section about interfaces, I will show you a better way to implement this code. For now, let's just move on. So let's recap. First of all, I'm going to put this class in a separate file. So Alt and Enter again. All right, let's recap. We have the Amazon class library, which is going to be our DLL, with two classes, customer and rate calculator. Rate calculator simply has a calculate method and returns 0. In the customer class, as part of promoting, we use the calculator object to calculate the rating. Now, let's clean this up. Back to our program. Here we have the customer object, right? I just noticed a problem here that when we drag and dropped the customer object from Access Modifiers project inside Amazon, it was not deleted from the source. I think I made a mistake while recording. So I'm just going to delete this class. All right, now in our program, which is in the Access Modifiers, see, customer is not detected. So we put the cursor here, and ReSharper has this red icon here. If we press Alt and Enter, we can activate that. So it's suggesting to reference Amazon. What it does is it goes to the references folder and adds a reference to Amazon. If you don't have ReSharper, what you need to do is, let's delete that and delete the using statement on the top. So see, the customer class is not detected. You simply right click on references, add a reference, then expand solution. See, in our solution, we have another project called Amazon. I select that and click OK. So now we have a reference to that assembly, to that class library, and we can use any of its classes. And now, to use the customer, we simply go on the top, type using Amazon, because that's the namespace. So you see, with ReSharper, it's much easier. You don't have to do all these manual steps. All right, let's move on. Now, let me show you that in the main method here, if we type Amazon, which is the namespace, dot, we see two classes, customer and rate calculator. In this case, rate calculator is used as part of promoting a customer. So we can argue that it's the internals of the customer or the Amazon domain. And based on the encapsulation principle of object-oriented programming, we shouldn't reveal the implementation anywhere in the code. So the problem is, if we use this rate calculator here, calculator. Now this project, our access modifiers, this program class in the main method, we have a dependency to this calculator object. In the future, if we go to our Amazon class library and decide to get rid of this rate calculator, let's remove this class here. The areas that are affected, one is inside the customer class here, but we also have this line in somewhere else in the code that is broken. And that is not good, because this way we could have 10 other places in the code where there is a dependency to rate calculator, which is about implementation. If we declared this rate calculator as internal, it would have been visible inside this class library here, but not anywhere else in the code. So let me add that rate calculator back here. So I add a new class, rate calculator, and put that calculator method back, calculate, return 0. Now this time I declare it as internal. What happens is, in the customer class, this class is visible because it's part of the same assembly. But after this assembly, when we go to access modifiers, we cannot access this class. With the red underline, it says cannot access internal class rate calculator here. Well, that's pretty much for this lecture. I hope you enjoyed it, and thank you for watching. Okay, earlier in this course, in the section about classes, you learned about constructors. In this lecture, we're going to learn more about constructors and inheritance. There are two things you need to know about constructors when it comes to inheritance. First is that during the instantiation of an object, the base class constructors are always executed first. And the second is, base class constructors are not inherited. So in a derived class, you need to redefine your constructors. It's easier to explain these with an example. So here we have a vehicle class with a private field called registration number. The vehicle class has a constructor that takes a parameter of type string called registration number. And we use this argument to initialize the private field here. Now let's say we would like to create a class that derives from vehicle. So our class can look like this, a car class that derives from vehicle. Note that I have redefined a constructor with a string parameter for the registration number here. The reason for that is, even though we defined a constructor in the vehicle class, it's not going to be inherited by the car class. So we need to redefine that constructor here. But what are we going to write in this constructor? Well, I've highlighted this line with red, which means this is not valid. In fact, if you write this code, it's not going to be compiled. You're going to get an error. Why? Because in the vehicle class, we declared registration number as private. Let's take a look at the vehicle class again. So note that the registration number is declared as private, which means it's not going to be accessible in the car class. And in the lecture about access modifiers, I explained why private is a better choice than protected. So back to our car class. At this point, we are not going to be able to access the registration number field because it's the implementation detail of the base class, which is vehicle, which we would like to encapsulate in the vehicle class itself. So that detail is not leaked anywhere else in our program. Now, instead, if we declare that as protected, just let's say for argument's sake, we would be able to access that field here, but still it's not a good idea to initialize that field here, because we defined this concept somewhere else in the code, in the vehicle class's constructor. So we should not repeat ourselves. Instead, what we need to do here is to reuse that code we wrote in the vehicle class's constructor. How we do that is using the base keyword. So all we need to do here is, when declaring the constructor for the car class, before opening the body of the method here, we append colon, base, and here base is simply a way to access the base class. This syntax simply represents a method call. Imagine you're calling a method called base, and here you're passing an argument to that method. That method is simply the constructor of the vehicle class. So the constructor of the car class receives an argument called registration number, and here we simply pass it to the base class's constructor. And in the constructor of the car class here, we should write anything specific to the initialization of the car class itself. Okay, now let's start coding and see these concepts in action. Okay, I'm going to show you a few different things here. First, let's start by creating a vehicle class. So, public class vehicle. Let's create a default or parameterless constructor. So, ctor tab. And here we use console.writeLine to log a message to the console. So, cw tab. Vehicle is being initialized. Now let's define a car class that derives from vehicle. And again here, we define a constructor that simply logs a message to the console. So ctor tab console.writeLine car is being initialized. Okay, now to clean up our code, we put these classes in separate files. So we go here, Alt and enter, enter, Control minus, back here. Again, one more time, back to program. Now here we create a car object. So var car equals new car. There you go. Let's run this application. Note that we got two messages on the console. First one is vehicle is being initialized, and the second one is car is being initialized. So what you see here is when you create an object, the constructor of the base class is always executed first. Okay, now let's extend this example and take a look at the base keyword. We go back to our vehicle class. So I'm going to leave this default constructor here, but I'm also going to create another constructor that takes a parameter called registration number. So ctor tab. This one is going to take a parameters. So string registration number. And here we can use Alt and enter. And the first item is introduce and initialize field registration number. And as you see, what happens is ReSharper automatically creates a private read-only string field called registration number. If you like this kind of fast coding techniques, I have a course called Double Your Coding Speed, where I teach you lots of techniques to write code faster and easier. So back to our example here, the vehicle class has two constructors. One is default or parameterless, and the other one takes a parameter of type string. Now let's go to our car class. See, at this point, everything is fine. The reason for that is the vehicle class has a default or parameterless constructor. So we can create an object of type car, and at this point, first the default or parameterless constructor of the vehicle is executed, and then this constructor here will be executed. But let's see what happens if we go to the vehicle class and comment out this default constructor. Now back to our car class. Look, we got a red underline here. And the error is saying base class vehicle doesn't contain a parameterless constructor. What does this mean? Basically, what's happening here is when we create an object of type car, the runtime first tries to create an object of type vehicle. But because the vehicle type does not have a default or parameterless constructor, the runtime doesn't know how to create an object of type vehicle. So what we need to do here is, back to the car class, we use the base keyword to call one of the constructors of the vehicle class. And how we do it is very simple. Enter, colon, we use the base keyword, open brackets, and here we go. We have one constructor that takes a string parameter called registration number. Now at this point, we need to supply some value. We can simply hardcode something here, but it's not a good idea because we don't want to hardcode a registration number here. A better way is to receive a parameter called registration number in the car class's constructor. So here, string registration number, and whatever we receive here, we simply pass it to the base class. There you go. Now let's modify the message we log on the console to see the order of execution in more detail. So what I'm going to do is I simply add the registration number here. Registration number. And we do a similar technique in the vehicle class's constructor. Vehicle is being initialized, and here the parameter is going to be registration number. Let's run the application again. We had a builder. Let's see what's happening here. Double click here. Here the error says car does not contain a constructor that takes 0 arguments. So what's happening here is we changed the constructor of the car class to receive an argument, but here we forgot to supply one. So let's just add a registration number, XYZ1234. We run the application. Again, note that the vehicle is being initialized first and then the car is being initialized. And in both constructors, we receive a parameter, and that is what we passed here during instantiation of the car object. Well, that's pretty much it for this lecture. I hope you enjoyed it and thank you for watching. Okay, at this point you know how to use inheritance in C#. When you have a base and a derived class, there are situations where you need to convert an object to a base or a derived class reference. And that's what we're going to learn in this lecture. So I'm going to talk about conversion from a derived class to a base class, which is referred to as upcasting. And then I'm going to talk about the opposite. So from a base class to a derived class, which is referred to as downcasting. And finally, I will explain the as and is keywords. So let's assume we have a class called shape and a class called circle that derives from the shape. To keep things simple, I have excluded the members of these classes in this example. Okay, now let's talk about upcasting. In this example, we have an object called circle, which is of type circle. As you see from this example, in C#, we can convert an object like circle to its base class reference, in this case, shape. No conversion is required, so it's implicit. And now let's look at downcasting. So following from our last example, we can convert shape to a circle object using an explicit cast, as you see in the example. Now, one thing you need to be cautious about is that casting can throw an invalid cast exception. In this example, our shape object is actually pointing to a circle object at runtime. So we can cast it to a circle. But if we try to cast it to another type, like a car, it's going to throw an exception. So here's an example. We cannot cast shape to a car, and that throws an invalid cast exception. Now, to prevent this from happening, we can use the as keyword. So imagine we have an object and we would like to convert it to a car. With explicit cast, as you see here, we may get an exception. A safer way is to use the as keyword. So when we use the as keyword, if the object cannot be converted to the target type, we are not going to get an exception. Instead, what is returned will be null. So in the next line, we can check if the result is not null, and then we can do whatever we want with that object. We also have is keyword. With the is keyword, we can check the type of an object. So we can say if object is a car, then we can safely cast it to the car. Otherwise, we won't do any casting. Okay, let's jump into code and see all these concepts in action, plus some real-world examples of where you need to do conversion between objects. Okay, we're going to see a few interesting and useful things in this video. Let's start by creating a class called shape. So, public class shape. The intention here is to model an application like PowerPoint or Keynote on Mac. So we have the concept of shape, which is going to be common across other concepts such as text, table, image, whatever. So each shape in our PowerPoint application is going to have at least a width and height. So we create two properties, width and height. And at least it needs a position. So we can have an X and Y. We also need a method to draw a shape. So public void draw. To keep things simple, I'm just going to leave out the implementation for now. So let's move our shape class to a different file, just like we've done in other exercises. Alt and enter, enter. Back with control and minus. Now let's create a class called text that derives from shape. Now our text class needs some additional properties like font name or font size. So font size and font name. Again, we're going to move this class to a separate file. So back to our program. Now let's create an object of type text. Text equals new text. Now I want to show you upcasting. So we can declare a variable of type shape and simply assign it to text. As you see, no conversion is required. So we can implicitly convert an object reference like text to its base class reference like shape. And this is very powerful. I'm going to show you how we're going to use that in real-world applications. But before we get there, let me tell you a little bit more about what is happening behind the scene. Both these text and shape objects are actually pointing to the same object in memory. Well, it's more accurate to say text and shape are both references to the same object in memory, but they have different views. What it means is, if I go here and say text dot, I can see all the properties of a text object. So font name, font size, plus the ones inherited from the base class. But if we use the shape reference, we see a more limited view. So as you see, font name and font size are not there, even though at runtime, the object that we have in memory does have those properties, but we are not going to see them if we use the shape reference. Now you might wonder, why do we need a more limited view of an object? We'll get there. I'll explain that in a real-world scenario. But for now, let's just do a simple experiment. So what I'm going to do is, first I use the text object and set the width to 200. Now I use the shape reference and modify that width to 100. Finally, I'm going to display the width of the text on the console. So console.writeLine, text.width. What value do you think we're going to get on the console? 100. Because both text and shape are references to the same object. They just have different views. Let's run the application and verify this. There you go. So we got 100. Now, what's the point of converting an object reference to its base class reference? Well, this is actually very powerful. And that brings us to a new topic called polymorphism, which we're going to see in the next section. But for this video, let me give you some insight about where we're going to use this kind of conversion in a real-world scenario. Well, first of all, let me clean up all this code here. Okay, in .NET Framework, we have a class called StreamReader, which we use to read data from any stream of any kind. So let's create an object of type StreamReader. So StreamReader reader equals new stream reader. Okay, note that here we have a few overloads for the constructor of this class. The simplest one is the one that takes a stream object. In .NET Framework, stream is the base or parent of every kind of a stream. For example, file stream or memory stream. Let's take a look at them in the object browser. So we go to View and then Object Browser. In the search box here, let's type file stream. So here's our file stream class, which is defined in system.io namespace. Here's the declaration of the file stream class. Note that it derives from stream. And here are the members of the file stream. So we use a file stream object to work with a file. It has methods to read from a file or write to a file. Now let's take a look at memory stream. So back here, search for memory stream. Again here in the declaration of memory stream, note that it derives from stream. Now let's get back to our program. In practical terms, in the constructor of a stream reader, we can pass any object whose type derives from the stream class without any conversion. So what we can do here is we can simply pass a new file stream, or we can pass a memory stream. So any class that derives from the stream class. So back to our upcasting concept, the object we send here will automatically be upcast to its parent class, which is stream. Let's take a look at another example. So I'm going to comment this out. We have a class called ArrayList, which we can use to store objects in a list. So ArrayList, list equals new ArrayList. Or we could use var here to keep our code cleaner. Now let's take a look at the add method. The add method takes an argument of type object. And remember, object is the parent of all classes in the .NET framework. So essentially, what we can do here is we can pass any object to this add method. And no conversion is required. So I can add a number here, or I can add a string, or I can add a text object, and all of these objects will be implicitly converted to the base object class. Now, in real-world applications, we should not really use the ArrayList class because it's not a type-safe kind of list. As you see, we can store a different kind of object in every element. So in this example, the first element is a number, the second one is a string, and the third one is a text object. So at runtime, we may get exceptions as a result of converting array elements to target types. A better way is to use generic lists. So we can use a generic list class like var, let's call it another list, equals new list. This is a generic class. A generic class takes a parameter which is used to enforce some kind of constraint on that class. So for example, if I put integer here, my list is going to be a list of integers. So every element in the list is going to be an integer. Or we could use a list of shapes, which means every element is going to be of type shape. So we can store a shape object or an instance of any of its derived classes. Okay, so that's all about upcasting. Now let's take a look at downcasting. So let's clean up all the code here. I'm going to declare a shape object. So shape. And now I can assign it to a text. So even though at compile time, the type of our shape object here is shape, at runtime, its type will be text. Let me show you what I mean by that. So I put a breakpoint here using F9. I run the application in the debug mode using F5. Now we press F10. Okay, here in the watch window, let's clean up whatever we had here. So I just type shape. So this is a way to watch objects and their content in C#. So as you see, our shape object is actually of type text, even though I declared it as shape. Now the problem with this shape object is, if we type shape dot, we get a limited view, as I explained earlier. So we are not going to be able to access the properties defined in the text object. So that's where we need to downcast the shape object. So what I would do is I declare a text, call it text, and I apply a cast here. So I want to convert shape to a text. Now, with this object, we have access to every property in the text class, like font name or font size. Now you might wonder, what is a real-world example of having to downcast objects? Well, to demonstrate that, I'm going to close this project and create a new project. I'm going to use WPF application, or you could use Windows Form application. Either of these are used to build desktop applications for Windows. So let's go ahead with WPF application. I leave the defaults in terms of name or location. It doesn't really matter. Okay. Okay, here's our designer. And as you see, we have a blank form. So if you run this application, we're just going to see a blank form. There you go. So just a blank form. Let me close that. Now what I want to do is to put a button on this form. So from the toolbox, find under Common WPF Controls, drag and drop button here. Now double click that. The designer creates a method here called button_click. This method will be executed when the user clicks on the button. We can just display a message here, messagebox.show hello world. Let's run the application. So I click the button and we got this hello world message, right? Okay, now let's take a look at the parameters of this method. The first one is of type object, and it's the sender or source of that click event. In this case, that's going to be a button. But the problem is, if I type sender dot, I don't see any properties or methods related to the button class. All I see are the members defined in the object class. This is a very common case where you need to downcast an object. So we can do a cast to a button and store that in a separate variable like button. And here we have access to all these properties and methods of the button class. There you go. Now note that in this example, because I was sure that this method is the click handler for a button, it's safe to cast it to a button like this. But if there are situations where you're downcasting an object and you're not sure about the runtime type of an object, that's where you use the as keyword. So alternatively, we could do sender as button. And then if button is not null, here we could have any code that requires to access a button object. So at this point, I know the conversion was successful and I can type button dot actual height. Let's put it on in a message box. And we need to convert that to a string because actual height is a number and the show method of the message box requires a string. So let's run this application. I click the button. Note that we got 21.96. Okay. And now we got the second message box, which is the hello world. Okay, well, that's pretty much it for this lecture. What I want you to take away is, in C#, upcasting is implicit. So you can simply convert an object reference to a base class reference. In practical terms, that means wherever a method requires an object of a given type, you can pass an object of that type or any types that derives from that type. The second thing I want you to take away from this lecture is, in situations like handling the click of a button or anywhere where in your method you get an argument, and that argument gives you a limited view to that object, you can use downcasting to convert that object to a more specific type. And to do that, you can use an explicit cast or the as keyword. I hope you enjoyed this lecture and thank you for watching. Okay, we got to boxing and unboxing. In this video, I'm going to talk about the concept of value types and reference types, and from there will lead to boxing and unboxing. So all types in C# are divided into two categories, value types and reference types. Value types are stored on the stack. What is the stack? When your program is executed, a limited amount of space in the memory is allocated to each thread of your program. And this space is used to store simple values, like all primitive types like byte, integer, float, char, bool, as well as the struct type. Values stored in the stack have a short lifetime, which means as soon as they go out of the scope, they immediately get kicked off the stack by the runtime. We also have reference types. Reference types are stored in the heap, which is a larger amount of memory. We use heap to store objects that require a longer lifetime. Examples of reference types in C# are basically any classes. So the object class that is the parent of all classes, or the array class, or the string class, or let's say we have a custom class called dbMigrator. These are all examples of reference types. Now, why does it matter? Well, earlier in this section, we learned that an object reference can be implicitly converted to a base class reference. And here's the example I showed you. So here we create an instance of a circle class, and then we can simply assign it to a shape reference. So this object reference can be implicitly converted to its base class reference. No conversion is required. We also learned that the object class is the base of all classes in the .NET framework. So taking the last example, we can modify it to something like this. So since the object class is the base of all classes in the .NET framework, we can simply point it to any objects. And that object reference will be implicitly converted to the object reference. Now that brings us to an interesting scenario, where we put a value type on the right side of the assignment operator. And this is what we call boxing. So in a formal definition, boxing is the process of converting a value type instance to an object reference. So as an example, here I have a number that is of type integer. And since object is the base of all classes in the .NET framework, we can declare an object variable and assign it a value type as you see here. Or a different way to write the same code is like this. You simply declare an object variable and assign it a value. What happens behind the scene is this value gets boxed by the CLR and stored in the heap instead of the stack. So let's take a look at the memory visualization. So assuming that here we have a stack and a heap, and on the stack we have a variable called number with the value of 10. Now when boxing happens, CLR creates an object in the heap and then creates a reference in the stack that points to that object. So as you see, the value is now stored in the heap along with an object reference in the stack. Unboxing is the opposite of boxing. So in this example, we have object that is assigned 10. So at this point, boxing happens. Now when we cast that object to an integer, unboxing happens, and the result is we get a new variable on the stack called number with the value of 10. What you need to know about boxing and unboxing is that they both have a performance penalty because of that extra object creation. And that's something you should avoid if possible. It's best to show this with an example. So let's start coding and see boxing and unboxing in action. Okay, earlier I told you about the ArrayList class. Let's create an object of type ArrayList. Now let's take a look at the add method. As you see, the add method takes an argument of type object, which means because the object class is the parent of all classes, we can pass any objects here. So I can pass a number here, or a string, or a date time, or anything. Now there are two problems with the ArrayList. The first one is type safety. As you see, each element here has a different type. So we lose type safety, which means at runtime, if I try to get the second element of this list and cast it to an integer, we're going to get an exception. So let's declare a variable called number and get the second argument of this list and cast it to an integer. Now the second argument is of type string. So if we do casting here, we're going to get an invalid cast exception. So that's one problem with the array list. But there is another problem. The problem is the add method takes an argument of type object, which means if we send a value type here, boxing will happen. And subsequently, when we get that value back and cast it, unboxing happens. So in this example, 1 is an integer, it's a value type, and here we get boxing. String is a reference, and in this case, boxing is not going to happen. And datetime is a structure, as you see here. A structure is also a value type. So again, here, boxing happens. A better way is to use a generic list. So instead, let's create another list and use the generic list here. And let's say we want to store a list of numbers. So we pass integer as a generic parameter. This generic list class is defined in system.collections.generic namespace. And now let's take a look at the add method. So another list.add. Look, it receives an argument of type integer as opposed to object. So we get type safety, which means every element is going to be an integer. And no boxing will happen because internally this list stores a list of integers, not a list of objects. Let me show you another example. So this time I create a list of names and I use a generic list of string. Now if we access the add method, every element is a string. Again, we have type safety and no boxing. So the lesson is when you're working with a class, if you're calling a method and that method gets an argument of type object, be aware that if you pass a value type there, boxing is going to happen. And this has a performance penalty. It's better to use a generic implementation of that class if it exists. Well, that's pretty much all you need to know about boxing and unboxing. I hope you enjoyed this lecture and thank you for watching. Okay, we got to method overriding. In this lecture, I'm going to talk about what is method overriding and introduce you to two powerful keywords in C# called virtual and override. Method overriding is simply modifying the implementation of an inherited method. What does it mean? When we use inheritance, there are times that we may want to modify the implementation of a method that we inherited from a base class. Maybe that implementation doesn't apply to a derived class. That's where we can use method overriding. So we override the implementation of an inherited method. Sometimes developers new to C# get confused between method overriding versus method overloading. Overloading is having a method with the same name but different signatures. Overriding, on the other side, is about changing the implementation of an inherited method. Let's take a look at an example. So throughout this course, you have learned about the shape class. So it's the base class for our imaginary PowerPoint application. A shape class can have properties like width, height, position, and so on. And it can also have some methods. To keep things simple, I've only added the draw method here. Now, when we derive a class like circle or image from the shape, the algorithm we use for drawing a circle or an image is different. So that's where we need to change that implementation of the draw method that we inherited from the parent shape class. Doing this in C# is very simple. And that's where we use the virtual and override keywords. So we can change this example to something like this. So all we do here is we decorate the draw method in the base class with the virtual keyword. And that gives us the ability to change that implementation in a derived class. And to do that, we use the override keyword in the derived class. Note that you don't necessarily have to override or change that implementation, but if you want, you can do so by applying the override to that draw method in the derived class. If you don't override that method, the default implementation defined in the base class will be inherited. Now, this technique is extremely powerful, and that's one way to implement polymorphic behavior in C#. Now I want to keep theory in this lecture to minimum and focus on practicality. So let's start coding and see polymorphism and method overriding in action. Okay, the example I'm going to show you in this lecture, I believe is an eye-opener. So let's take a look at this piece of code I have written, which is an example of a poorly written piece of code. Then I will show you how to change this code and make it much better. So let's take a look at the classes we have in this project. We have a class called shape, which has a few properties like width, height, a position, which is simply an x and y, and an enumeration called shape type, which determines the type of that shape. Let's take a look at the shape type enumeration. So shape type is an enumeration, and currently we have support for circles and rectangles. We also have a class called canvas. Here's our canvas class. So this class simply has a method called drawShapes, which receives a list of shapes. Inside this method, we iterate over the list of shapes, and then we do a switch on the type of the shape. So if the shape type is circle, here we have an algorithm that draws a circle. Or if the shape is rectangle, here we're going to have the algorithm for drawing a rectangle. Now this code has a problem. And even though it's a classic example that I'm using for teaching, I've seen the exact same pattern in many real-world applications. So let's see what's the problem with this code. The problem is that next time we decide to add support for a different type of shape, let's say a triangle, we have to go here to shape type enumeration, add a new member here, triangle, and then we have to go modify the canvas class. Here we're going to have another case statement like case shape type dot triangle, and of course here we're going to have some algorithm for drawing a triangle. The problem is every time we define a new shape type, this method is going to be changed, and as a result, the class that contains this method has to be recompiled and redeployed, which means any class in the application that is dependent on this class also needs to be recompiled and redeployed. Same for the shape type. Every time we modify this enumeration and add a new member, any classes that is referencing this, again, is going to be recompiled. So there is a lot of tight coupling here. And there's also another problem. Take a look at the canvas class. Imagine if you're going to have support for 10 different types of shapes. This method is going to get really fat. Well, you may argue that we can refactor some of this logic here into separate methods, but still the parent method here, drawShapes, is going to be fat and complex. Now, the reason we have this problem with this code is because the shape class itself has only properties. It doesn't have any behavior. It doesn't have any methods. Back to the encapsulation principle of object-oriented programming, we want to encapsulate data and behavior or methods in the same unit. That's a class. Applications designed or developed this way, like the one you see here, have data somewhere, whereas behavior is somewhere else. In this example, data is here, but behavior is inside this canvas method. So we need to encapsulate them into one unit. So let's see what's a better way to write an application like this. So the first thing is I'm going to create a new class called circle. Currently, we don't have inheritance here. We just have a shape class that has a type. So let's create a circle. And we derive it from shape. And another class. Rectangle is also a shape. Now I'm going to get rid of this enumeration here because I want the concept of type of shape be determined in a derived class. So circle is a type of shape. Rectangle is a type of shape. We don't need the shape type enumeration anymore. So let's remove this. And obviously I remove it from the solution here as well. Now back to our canvas class. Obviously this code is broken because the enumeration doesn't exist anymore. And that doesn't matter at all. Because as I explained, here is the behavior around the concept of a circle. So we need to encapsulate that behavior and the data related to that behavior in one unit. So we go back to our circle class here. First, we need to add a method here called draw. So the draw method defines the concept of drawing a shape. Now this method will be inherited by these derived classes. But how we draw a circle is different from a rectangle. The algorithm is different. And that's where we use method overriding. So we declare this method as virtual, so we get a chance to change its implementation in a derived class. So here I go to the circle class. We simply type override, and note that Visual Studio automatically lists all the methods that you can override. So here is the draw method. And here are 3 methods that we have inherited from the base object class: equals, get hashcode, and toString. I will show you an example of overriding one of these methods later. So let's just get back to our draw method here. Now by default, Visual Studio automatically adds this base.draw method call here. What does it mean? Base is a reference to the parent class. So here we can write any code specific to the circle class itself. And then before or after, if we need to, we can pass the execution to the draw method defined in the parent class. In this example, we don't really need this because the draw method we have in the parent shape class has no implementation. It's just an empty method. So remove this. And here I will have the algorithm for drawing a circle. Let's get back to our canvas class. Note that here is the algorithm for drawing a circle, which was not encapsulated with the data about circle in one unit. The behavior was different somewhere else in the application. And that's a symptom of poorly designed application. So I just cut this from here and put it back here. We do a similar technique with the rectangle class. So overwrite, tab, and enter. We don't need this line. Now let's get back to the canvas and grab this line, which is for drawing a rectangle, and paste it here. Now let's go back to the canvas again. So we don't need the circle and rectangle anymore. And let's say currently our application does not have support for triangle. Then I will show you how we can add support for triangle without breaking existing code, without the need to recompile and redeploy many classes. So let's get rid of all this switch block here. Now inside the for each block, what we do is we simply call the draw method of the shape. And here's where the magic happens. Let's take a look here. So the parameter for this method is of type list of shapes. So every element of this list is going to be a shape object or an object whose type derives from the shape class. And that's what you learned earlier. So at runtime, what happens here is we iterate over this list of shapes, but we may have a circle in the first element of this list, or the second element might be a rectangle. So when we call this draw method here, even though we are talking about shapes, at runtime, that shape object might be a circle or a rectangle. So when we call the draw method, the draw in the circle will be called, or the draw in the rectangle will be called. And this is what we call polymorphism. So poly in Greek means many. Morph means form. Polymorphism means many forms. So you see we have the concept of shape and the concept of drawing a shape, but that concept can have different forms depending on the objects we have at runtime. Let's get back to the canvas class again. Look, the implementation here is very simple. Okay, now let's go to the program class. Okay, here in the main method, first we create a list of shapes. Then we create a canvas and we pass the list of shapes to the draw shapes method of the canvas. Previously, I used the type enumeration. And that's why, because I deleted the type enumeration, this code is now broken. Basically, what we need to do here is to store different types of shapes in this list. So I want the first object to be a circle. So let's add a new circle here. And let's not worry about setting the properties. And here, let's put a rectangle. Now to show you exactly what happens at runtime, I put a breakpoint here with F9. Run the application in the debug mode with F5. Now we can step into this method with F11. Okay, now let's put a watch on the shapes object passed to this method. So in the watch window, type shapes. So that's a list with two objects. Let's expand this list. Note that the first object is a circle and the second one is a rectangle. Again, because it's a list of shapes, an element in the list can be a shape object or an object whose type derives from the shape. Okay, let's collapse this. Now we continue execution with F10. One more. Now we are inside the for each block. Let's put a watch on the shape object. So here is the current shape. And as you see, it's a circle. Let's continue execution with F10. Now we step into this method with F11. Note that now we are inside the draw method of a circle. So let's continue execution with F10. One more. Now this iteration is over. Let's continue execution. Here's the second iteration. And note that in the watch window, now our shape object is referencing a rectangle. So if we continue execution here, now we step into this draw method. That takes us to the draw method of the rectangle. Okay, now let's stop the debugger with Shift and F5. So back to our canvas class. Again, I want to re-emphasize this one more time. So even though here we are dealing with a list of shapes, at runtime, the objects we have in the list can be a shape or any object whose type derives from the shape. Now, because we declared the draw method in the shape class as virtual, that gives us the ability to override it in derived classes, which means at runtime, if this shape is a circle, the draw method of the circle will be called. Or if it's a rectangle, the draw method of the rectangle will be called. Now, what's the benefit of this approach? There are a number of benefits. The first one is, if you remember previously, we had various algorithms in this draw shapes method. We had algorithm for drawing a rectangle, we had algorithm for drawing a circle, and imagine as we add support for more shapes, this method is going to get fatter and fatter. We fixed this problem by using encapsulation such that we encapsulate the concept of drawing a circle as well as the attributes or properties about the circle in one unit. So here, if you want to have some extra properties about the circle, we can define them here. All these members in the circle class are highly related. So pieces of the code that are related are in one unit, as opposed to all over the place. So this way, the circle class doesn't get bulky because it only knows about the concept of circle. Similarly, the canvas class doesn't get bulky either. The implementation is very simple. Now, tomorrow, if we decide to add support for a different type of shape, let's say triangle, this method is not going to change. Let's see what happens. So we go back here to our shape file, and let's create a new class. Call it triangle and derive it from shape. And now override the draw method. And here we implement the algorithm for drawing a triangle. So console.writeLine, draw a triangle. Now the interesting thing here is we simply added a new class called triangle, but this had absolutely no impact on the shape class because shape class knows nothing about triangle. It also had absolutely no effect on the rectangle. Rectangle is not changed, it's not affected. Same for circle. And same for canvas. Our canvas class only knows about the shapes. Whatever shape they are at runtime, who knows, who cares? The canvas doesn't have to worry about it. So this way, with polymorphism, we can create new shapes by simply creating new classes, and that has absolutely zero impact in our existing classes. And this is a sign of loosely coupled applications. Well, that's pretty much it for this lecture. I hope you enjoyed it, and thank you for watching. So we got to abstract classes and members. In this video, I'm going to talk about the abstract modifier that can be applied on classes and their members, including methods and properties. And then I will tell you about the rules that you need to know about abstract classes and members. So what does the abstract modifier do? The abstract modifier indicates that a class or a member is missing implementation. It's easier to explain this with an example. Here's the example we had earlier in this section. So we have a shape class with a draw method that is declared as virtual. And we have a circle class that derives from the shape. In the circle class, we override the draw method. And here we provide the implementation for drawing a circle. Now here we have a problem. The problem is that it's hard to define an implementation for drawing of a shape. How do we draw a shape? It doesn't make sense. When we're talking about a circle, we know how to draw a circle. Or when we are talking about a rectangle, we know how to draw a rectangle. But it's impossible to define how to draw a shape because the concept of shape is too abstract. In situations like this, a better approach is to use the abstract modifier. So we can declare the draw method as abstract to indicate that this method is missing implementation. And we leave it to the derived classes to provide an implementation for this method. So to use the abstract modifier, the code changes to something like this. Note that here the draw method is declared as abstract, and that's the reason it doesn't have implementation. So it doesn't have a body. It's just a declaration. And here we terminate the declaration with a semicolon. When we declare a method or a property as abstract, the class that contains that needs to be declared as abstract as well. So here, the shape class is declared as abstract. With this declaration, we are telling that the shape class is missing implementation and that implementation needs to be provided by its derived classes. In a derived class like circle, it simply override the abstract methods in the base class. So abstract methods are inherently virtual and can provide polymorphic behavior, as you have seen earlier in this section. Okay, now let's review a few rules that you need to know when working with abstract classes and members. The first one is that an abstract member cannot include implementation. So as you saw in the previous example, the draw method didn't have a body. It was purely a declaration. The second rule is that if a member is declared as abstract, the containing class needs to be declared as abstract too. The third one is that in a derived class, you must implement all abstract members in the base abstract class. So in this case, our shape method had only one abstract method, that was draw. If it had 3 abstract methods, you had to override all these 3 abstract methods. And the last one is abstract classes cannot be instantiated. So when we declare the shape class as abstract, we cannot create a new instance of shape. So this line will not compile. Now you may wonder, why do we use abstract? What's the benefit? You use abstract when you want to provide some common behavior while forcing other developers to follow your design. What do I mean by that? Well, in our shape example, by declaring the draw method as abstract, we'll make sure that anytime a developer derives a class from the shape, they will provide an implementation for the draw method. If we did not declare this method as abstract and instead provided an empty virtual method, we would run into the risk of a developer deriving a class from the shape without overriding the draw method. In that case, drawing that object would not make sense. It's easier to demonstrate that in the code. So let's start coding. Okay, let's create our shape class first. I'm not going to use the abstract modifier yet because I want to show you the problem and then explain how the abstract modifier resolves that problem. So here our shape can have a few properties. Let's just give it a width and a height and a method for drawing the shape. So as I explained, we cannot define an implementation for drawing a shape. We have to leave this method as empty. Now let's put this in a separate file. Okay, back to our program. Now let's create a circle class. And here we override the draw method. Nothing new so far. So let's just put this in a separate file. Now imagine you're designing this as some kind of framework. So in your framework, you're providing the concept of a shape and a circle. In the future, other developers may extend on this topic. They may define new kinds of shapes. Or it doesn't have to be other developers. It could be yourself. So let's say sometime in the future, you decide to add support for a rectangle. So what happens is we go to the program, create a new class here, rectangle, and derive it from shape. But accidentally, we don't overwrite the draw method. Now let's see what happens. So we go to the main method, we create a circle, we draw the circle, and then we create a rectangle and draw the rectangle as well. Let's run the application. So here's the problem. We get a circle on the screen, but not the rectangle, because we accidentally left out the implementation. So here is where the abstract modifier can help. So we can go back to our shape class and say we have some common behavior or some common properties about the concept of a shape that we implement here, but there are behaviors here that we would like to leave to the derived classes to implement. The draw method is an example of that. So instead of creating an empty draw method here, we can just declare it as abstract. And of course, we need to get rid of the body and add a semicolon here. Note the red underline here. I put the mouse here. Abstract method in non-abstract class. Because the draw method is abstract, the shape class needs to be declared as abstract as well. Now let's add another method here that doesn't have to be abstract. Let's say every shape needs to have the ability to be copied into clipboard. So we can have a copy method here, which simply copies this shape to the clipboard. And perhaps this implementation would be common across all derived classes. We don't need to change that implementation in the circle or in the rectangle. So here we have some common code. Copy shape into clipboard. We could have other methods here like select. Perhaps when we select that shape in our PowerPoint application, we would like to display a highlight around the shape. Select the shape. Okay, now that we declared this draw method as abstract, let's take a look at the rectangle. So here's our rectangle class, and note the red underline. It says abstract inherited member draw is not implemented. So this way we create some kind of safety, some kind of guard. We make sure that everyone, including ourselves, follow the design. So what we do here is we put the cursor here. With ReSharper, we press Alt and Enter. And the first item is implement members. And ReSharper automatically creates override methods for any abstract methods derived in the base class. So let's implement this method here. Draw a rectangle. Now we run the application. Note that we get both draw a circle and draw a rectangle. So here's the benefit of abstract modifier. It's not something that you use every day in your programming career, but it's a tool that you can use when you're facing situations like this, when you want to force your design to be followed everywhere in the code base. Now, before we finish this lecture, I want to show you a couple more things. So first, let's put this rectangle class in a separate file to clean up our code. Back to the program. Look here, I cannot do something like this. We cannot instantiate shape because shape is declared as abstract, and that's the reason we get this red underline here. The tooltip says cannot create an instance of the abstract class shape. Here's yet another reason to use abstract, because what does a shape represent? It's too abstract. We cannot imagine a shape in our PowerPoint application. In our PowerPoint application, we have concepts such as circle, or rectangle, or image, or table. Shape doesn't make sense. We can just use shape as the base class that provides some common behavior, but it shouldn't really be instantiated. So let's comment this out. Okay, in the .NET framework, we have a class called stream, which is the base of all types of streams. Earlier in this course, I showed you file stream and memory stream. In case you missed that lecture, let's quickly review that here. So we go to View, Object Browser, and here we can type file stream. So file stream is a class that is declared in system.io namespace. And look at the declaration of this class here. So file stream derives from system.io.stream. Stream is an abstract class, which means you cannot instantiate it. Let's take a look at this class. Look, stream is selected here. Here you see the members declared in this class. And here's the declaration of the class itself. It's a public abstract class. Again, here is another example where some concepts needs to be declared as abstract. For example, what does a stream represent? A stream is too abstract, but file stream is very specific. It provides ways to read from or write to a file. Or memory stream is a kind of object that allows us to read data from memory or write data to memory. But the stream itself is just too abstract. So that's the reason the developers of .NET Framework have declared it as abstract. And by doing so, they have provided some common behavior that you can see in some of the methods here, but they left the implementation of some of the members to the derived classes like file stream or memory stream. Okay, that's pretty much it for this lecture. I hope you enjoyed it and thank you for watching. Okay, earlier you learned about abstract classes. Sealed classes are the opposite of abstract classes. So a sealed modifier prevents derivation of classes or overriding of methods. Similar to the abstract modifier, the sealed modifier can be applied to a class or a class member. If applied to a class, it prevents derivation of classes from that class. And if applied to a method, it prevents overriding of that method. Let's take a look at an example. So here's a circle class that you saw in the last lecture. It derives from the shape class and overrides the draw method. We can apply the sealed modifier to the circle class. By doing so, we cannot create a class that derives from circle. Or we can apply the sealed modifier to the draw method here. Note that sealed modifier can only be applied to methods that are overriding a virtual method on the base class. So if you're not overriding a method that is declared as virtual in your base class, there is no need to apply sealed. Now you may wonder, why do we need sealed? Well, the MSTN documentation states that sealed classes are slightly faster because of some runtime optimizations. But personally, I think that slight optimization is not going to make a difference in the performance of your application. In fact, sealed is one of those features that is hardly ever used. Personally, over the past 12 years of working with C# and the .NET framework, I've never felt the need to mark a class or a member as sealed. In fact, I think it's an anti-pattern. Because if you're going to apply sealed to some of your classes for a slight optimization, you're going to mess up with your inheritance hierarchy. So that can affect the design and the development. So as a guideline, I suggest to you not to use sealed unless you have a very strict reason for doing so. If you have made certain assumptions in a class and you don't want other classes to inherit from that class, that's okay, go ahead and use sealed. But another reason I added sealed in this course is because there are classes in the .NET framework that are defined as sealed, which means you cannot inherit from them. An example of that is the string class. You cannot inherit from the string class. So if you want to extend it, you need to use extension methods. Extension methods is an advanced topic, and I have covered it in my C# advanced course that you can find on Udemy. That's pretty much all you need to know about sealed classes and members. I hope you enjoyed this lecture, and thank you for watching. Okay, we got to interfaces, which is one of my absolute favorite topics. In this section, I'm going to talk about what is an interface, how to declare and implement interfaces, and then I will explain how interfaces improve the testability and extensibility of your application. So what is an interface? An interface is a language construct that is similar to class in terms of syntax, but is fundamentally different. Let's take a look at the syntax first. So here is how we can declare an interface. Instead of using the class keyword, we use the interface keyword. And note that in .NET, all interfaces start with the letter I. So wherever you see a type that starts with I, that represents an interface. It's a convention. But unlike classes, interfaces do not have implementation. So you see here, we have a method called calculate. That is simply a declaration. It doesn't have a body. It doesn't have curly braces. Also note that interface members do not have access modifiers. So here we don't have public, private, protected, whatever. Now you may wonder, why do we need a construct like that? Well, in simple terms, interfaces are used to build loosely coupled applications. That is an application whose components are not tightly related to each other. Which means making a change in one of these components is easier and has less or zero impact on other components. Let me use an analogy. Think of the concept of a restaurant and a chef. We can say a restaurant needs a chef with certain capabilities. By that definition, we can fill that role with anyone. Anyone who has those capabilities can fill the role of the chef for that restaurant. So the dependency between the restaurant and the chef is loose. If something happens to that chef, like he gets sick or he decides to move on to a different job, we can fill that role with someone else. Now, in contrary, if we said a restaurant needs John as a chef, that means we are very dependent on John. If something happens to John, if he decides to not to come to work, then the restaurant is in trouble. So this is a definition of a tightly coupled dependency. The restaurant is tightly coupled, tightly related, tightly dependent on John. Now, I use this analogy to explain that when building software, we want our classes or our components to be loosely related or dependent on each other. So if we decide to make a change in one of these classes, it has minimal or zero impact in other classes. Take a look at this picture. Here we have two classes, order processor and tax calculator. In this UML diagram, you see a dependency as demonstrated here between order processor and tax calculator. In C# terms, that means order processor has a field or a property that is of type tax calculator. Now, this is an example of tight coupling between order processor and tax calculator. If we make a change to this tax calculator here, it may affect the order processor and subsequently any other classes that depend on order processor. Now, we use interfaces to reduce this coupling. How? Well, we can change this picture to something like this. So instead of order processor being dependent on tax calculator, it's going to be dependent on an interface. That is iTax calculator. An interface, as you saw earlier, is simply a declaration. It's not a concrete class. It doesn't have code. Its methods do not have a body. So as long as we keep that interface the way it is, as in like we are not going to remove any of its methods or change its parameters, it's not going to have any impact on the order processor. Now, if we decide to change the algorithm for calculation of tax, we can create different classes that implement this interface here, and that would have absolutely no impact on order processor. If that concept is new to you, don't worry about it. I'm going to show you exactly how it works in code. Interfaces are extremely powerful, and once you really understand them, you're going to fall in love with them. So in the rest of this section, I'm going to explain how interfaces help improving the testability and extensibility of your application. So thank you for watching, and I'll see you in the next lecture. Okay, so in this lecture, I'm going to talk about interfaces and testability. I'm going to show you how interfaces improve the testability of your application. This lecture is heavily focused on coding, and we are not going to have any slides. So let's jump into Visual Studio and see how interfaces help improve the testability of applications. Okay, in this example, we're going to see a very basic hypothetical order processor. In a real-world application, this is going to be far more complex. But I have removed all that complexity here because we just want to focus on testability. So let's see what's happening here. We have an order processor here. We'll take a look at that in a few seconds. We also have an order object. And finally, we call the process method of the order processor passing the order object. Let's take a look at the implementation of this method. To get there, simply press Shift, Control, Alt, and B. There we go. So here's our order processor class. It has a field that is read-only and private. It's of type shipping calculator. So we use this calculator to calculate the shipping cost, as you will see shortly. In the constructor here, we instantiate this object. And here's our order processing method. So in the process method, we get the order object. First, you see an example of defensive programming. So first, I'm validating if the order is already shipped. If it's shipped, I don't want to ship it again. So a bit of defensive programming is good to have in your methods to make sure that you don't take the state of system to something that is unexpected. But on the contrary, if you're going to do too much defensive programming, your code is going to be bloated with too much validation. So at this point, I think it's just enough to see if order is shipped, then we throw an exception of type invalid operation exception, which states this order is already processed. Now, if the order is not shipped before, we simply create an object of type shipment and assign it to the shipment property. The shipment class has two properties, cost and shipping date. To calculate the cost, we use our shipping calculator. So we pass the order, and that shipping calculator knows how much the shipping cost should be for that order. For shipping date, I have hard-coded a rule here that states shipping will be done the day after the order is submitted. Again, this is a hypothetical scenario and it's most likely not the case in real-world applications. Now let's take a look at the calculate shipping method here. So simply put your cursor here, press Shift, Control, Alt, and B. Okay, in this method we have a simple rule. So if the total price of the order is less than $30, the shipping cost is going to be 10% of the total price of the order. Otherwise, if the order is $30 or more, we're gonna give a free shipping to our customers. So pretty basic. Now let's get back to our order processor. Okay, let's say we want to write a unit test for this process method here. If you have never done unit testing before, that's perfectly fine. I'm going to introduce you to the concept of unit testing briefly. Note that unit testing is a comprehensive topic and is way beyond the scope of this course, and I definitely plan to create a comprehensive course explaining the best practices of automated testing for C# applications. But at the time of recording this, it's not ready. In case you want to be notified about that course when it's ready, follow me on Twitter or Facebook or my YouTube channel. The details are in the introduction section of this course. Okay, let's move on and see what is unit testing all about. Unit testing is part of automated testing practice, which means we write code to test our code. So instead of we manually test our software every time using clicks and typing, we write some automated tests to achieve that. Now let's see how this happens in practice. So in Solution Explorer here, I'm going to right click and go to Add, New Project. In the left section under Visual C#, you see Test. So we select Unit Test Project, and I'm going to name it after my project.tests. So in this case, my project is called Testability, which is the name of this lecture. I'm going to name my unit testing project Testability.tests, or better, unit tests. In your project, whatever is the name of your project, just put that here instead of testability. Let's press enter. Okay, here we have a unit testing project. By default, Visual Studio creates a test class for you here, which is called Unit Test 1. Note that each test class has an attribute called test class, and it can have a bunch of methods like the one you see here, which are decorated with test method attribute. In C#, attributes represent metadata about your classes and their members. They don't have any logic, they're just markers. Then another application or another assembly can read this metadata and do something about it. For example, later you're going to see that we're going to use Microsoft Test Runner, and that test runner is going to look at all classes that have a test class attribute. And then it's going to run the methods that have a test method attribute like here. Okay, before we write our test, let's take a look at our order processor and see what kind of test cases we need to write. So back here, Okay, take a look at this process method here. Here we have two execution paths. One is if the order is shipped, we're going to throw an exception. The other one is if order is not shipped, we're going to change the state of the order by setting its shipment property to a new shipment object based on some values here. Now there is a problem here. The problem is that when we unit test a class, we need to isolate it, which means we need to assume that every other class in the application is doing its job properly, so we can write tests around this class. And that's why we call this practice unit testing. We are focusing on a single unit of functionality without dependency on any other parts. Now in this order processor class, we have tight coupling to shipping calculator. Look, here we have a shipping calculator which is instantiated in the constructor of order processor. So because of this tight coupling, we cannot isolate this class. So when we write tests for this piece of code here, this dependency to shipping calculator is going to be a problem. How do we solve that? Using an interface. So let's go to our shipping calculator class. This shipping calculator has one method called calculate shipping. We need to create an interface that has this functionality and then have this shipping calculator implement that. What does it mean? Remember the analogy I used for the chef? I said a restaurant needs a chef who has certain capabilities. Whether it's John or Mary or Steve, it doesn't really matter, as long as that person can fulfill some needs based on some standards. It's exactly the same scenario here. By using an interface, we're defining that role of calculating shipping. Now, which class is going to fulfill that role? It's a separate issue. In this case, this class is going to be fulfilling that role. It's like John being a chef. Now let's create an interface here. So similar to a class, public interface. We give it a name, iShipping calculator. Note that the name of the interface is prefixed with capital I, and that's a convention in .NET Framework. Now here we need a method called float calculate shipping, which takes an order object. Note that this method does not have a body like this. If you do that, you see this red underline here, highlighting an error. So let's undo that. Also, there is no access modifier here, so we cannot say public, private, whatever. See, it's not going to work. This interface simply defines the capability that a class should provide. Now, we need to have this shipping calculator class implement that iShipping calculator interface. How? We go here and type iShipping calculator. It looks a little bit similar to inheritance, right? But this is not inheritance. Because with inheritance, we write code once and then we reuse it. We don't have to type it again. But in this case, you see, we have this method declaration here, but we had to manually type all this code here. So this is not inheritance. We read this as shipping calculator implements iShipping calculator. Okay, now that we have this interface, let's go back to our order processor. Instead of being dependent on this concrete class, which is like John as a chef, we want to be dependent on an interface, like the role of the chef in a restaurant. So what I'm going to do is simply put this I here, and now we have an interface. And instead of creating a new object of shipping calculator here, we need to initialize this field using the constructor. Why? Because here, we're still dependent on that concrete shipping calculator class. So what we need to do is we go here, pass a parameter of iShipping calculator type, shipping calculator, and initialize our shipping calculator field using this argument. Look, now there is no reference to the shipping calculator concrete class. We're just referencing an interface. And this is an example of loose coupling. So if we go back to this shipping calculator class and we change its code, let's say we add a few new methods or change this logic here, it's not going to have any impact on our order processor class. Order processor doesn't know about shipping calculator. It just knows there is a class that can fulfill that need. Now, if we build our application at this stage, it's going to fail. Let's take a look. Control-Shift-P to build. Build failed. Let's double-click this error. Look, in the main method here, when instantiating an order processor object, we need to pass that shipping calculator. Look, it needs an instance of iShipping calculator. So here we need to specify that concrete class, which is shipping calculator. Now here you might be thinking, isn't that dependency to shipping calculator? Yes, it is, but it's in the main method here, which is outside that class. The main method here is like the matchmaker. It knows different concrete types and ties them together. But none of these concrete types, like the order processor, knows about the existence of other concrete types. So in this case, it's perfectly fine to instantiate this shipping calculator object here. Let's build again. Okay, the project is working. Now let's get back to our order processor and review our test cases. There you go. So the first test we need to write is if order is shipped, this method is going to throw an exception. Let's see how we write a test for that. So I'm going to open that unit test1 file here, which is inserted into the test project by default. I'm going to rename it. You can press Ctrl R and then R again, or F2. Because we are writing tests for order processor, the name of this class should be order processor tests. Now the name of this method should be based on a convention like this. We have the method name, underline, the condition that we're testing, underline, expectation. So here's the pattern. Let's see how it works. So in this case, the name of method we're testing is process. The condition is order is already shipped. And the expectation is throws an exception. So note that the method name is very descriptive. It can act as a documentation. Okay, now let's see how we can write a test for this class. So the class we're testing is order processor. Let's create an object of that type. So var order processor equals new order processor. Now, because I'm using ReSharper, I can easily press Alt and Enter here, and the first item is reference testability and use testability.orderProcessor. The reason for that is because here we are in a separate project, in our unit test project. We need to reference that project so we can use the classes defined there. So I'm just going to go ahead with ReSharper's refactoring. If you don't have ReSharper, you need to go here, right-click References, go to Add Reference, and then under Solution, under Projects, tick that testability. Okay, now here we have the order processor object, but we have to specify its dependency, which is iShipping calculator. Now, what do we need to pass here? We need to pass a fake object that is always working. We are not going to pass that original shipping calculator because we are trying to isolate that order processor, right? So let me create a fake shipping calculator. So public class fake shipping calculator. This class should implement iShipping calculator interface. Note this red underline here. That is here because we have not implemented this interface, which means we have not defined the methods that are declared in that interface. So for that to happen, you need to press Alt and Enter, and Enter. This shortcut always works whether you have ReSharper or not. Now you see we have this method called calculate shipping based on the declaration in that interface. And note that this method is automatically declared as public. If I change that to private, compiler is going to complain. Because methods declared in an interface should be public. So basically, as you see, an interface defines the public interface or the public functionality or the public service that a class provides. All right, in this method, I'm just going to hard code a simple number because we're not going to have a logic. We are assuming this fake class is doing its job properly, and our focus is on testing the order processor. We are trying to isolate it, right? So let's pass an instance of this fake shipping calculator here. And now I want to create an order that is already shipped. So let's create an order. How do we know if the order is already shipped? Let's go to the order class. Look, here I defined a property called isShipped that checks if the shipment object is not null. So if the shipment object is not null, this property is going to return true. So back to our test. What I'm going to do is simply, I use the object initialization syntax here, and at the same time I'm initializing the order, I also initialize its shipment property. Just set it to an empty object. This way, its ship property is going to return true. Now let's call the process method. So order processor.process and pass the order object. So here, what we need to assert is that an exception is thrown. With the default testing framework that comes with Visual Studio, you can achieve that using an attribute here. That's called expected exception. Here we need to specify the type of exception. So type of invalid operation exception. Note that here we are using Microsoft testing framework. If you're using other testing frameworks like NUnit or XUnit or whatever, the implementation could be slightly different, but the concept is exactly the same. We have to isolate a class using an interface. We need to arrange some preconditions. We need to act on a method, and then finally we need to do assertions. Okay, now let's run this test and see what happens. If you have ReSharper, the shortcut is Ctrl-T and R. Without ReSharper, you press Ctrl-R and then A. If you forget the shortcut, simply go to Test menu. This is Visual Studio's testing framework. Under Run, you see you can run all tests using that shortcut. With ReSharper, we go to Unit Tests and Ctrl-T and R as specified here. So let's run this. Note that we got a green tick here. Now let me show you something. If we go back, let me close this. If we go back to order processor and comment out these two lines here, and then go back to the test class and try to run this test again, note that this time the test failed and we got this red icon here. So the description here explains that this method did not throw an exception, which was expected from the process method. So let's close this. Back to our order processor class. Let's bring this back in. Okay, now let's write the second test case. So if the order is not shipped, we want to make sure that the shipment property is initialized properly. So we go back to our test class. Following the same pattern here, we're going to write another test method. Public void. The method we're testing is process. The condition is order is not shipped. What should happen? Should set the shipment property of the order. We decorate this method with test method attribute. Now we need to create an order processor object. So we can simply go here and copy paste this code here. This time I'm going to create a new order object, but I'm not going to initialize the shipment property. So is shipped is going to be false. And now if we call this order processor.process method, passing the order object, we need to assert that the order.shipment is initialized properly. To do that, we use the assert class that comes as part of the test framework. This class provides a bunch of useful methods for various kinds of assertions. First, we want to make sure that is shipped is set to true. So is true and we pass order.isShipped as an argument. We need a couple more assertions here. Let me scroll down so you can see this better. Okay, let's get back to our order processor. Look, apart from this shipment property being initialized, we also need to make sure that the cost is set properly and shipping date is set to tomorrow. Now in this case, because we isolated our order processor and passed a fake shipping calculator here, if you remember, that method always returns 1. So we need to assert that the cost is set to 1. And for shipping date, we can assert that it's set to tomorrow. So let's get back to the test method. Okay, I'm going to write another assertion here. So assert dot. This time I'm going to use the reEqual method. The first argument to this method is the value that we expect. So the cost should be 1. The second argument to this method should be the actual value, which is going to be order.shipment.cost. And we write a similar assertion around the date to make sure that the date is calculated properly. Assert.reEqual. The date should be tomorrow. So datetime.today.addDay 1. And the actual value, which is the second argument to the reEqual method, is order.shipment.shippingDate. Let's run this test. So the test passed. Okay, before we finish, let's recap. So back to our order processor. Previously, this class had a field of type shipping calculator, and because of that, it was tightly coupled to that implementation. We reduced this coupling by introducing an interface, iShippingCalculator. With an interface, this class is no longer dependent on a concrete class, which means we can isolate it during unit testing. So the takeaway from this lecture is, when you're trying to unit test your classes, if that class has other dependencies in terms of concrete classes, you can use an interface to reduce that coupling. Before we finish this lecture, let me show you a quick way to extract an interface from an existing class. So let's get back to our shipping calculator. Imagine we didn't have this interface before. So I'm going to get rid of it. So here's the original shipping calculator class. If you have ReSharper, you can press Ctrl, Shift, and R to activate refactoring options. But unfortunately, that shortcut is not working for me here because I'm using a Mac keyboard. So the alternative way is right-click the type here, go to Refactor. This is part of Visual Studio refactoring tools, and you will always have this whether you have ReSharper or not. Then go to Extract and extract the interface. In this dialog box, you see the name of the interface automatically populated for you, iShippingCalculator, and here you can tick all the members of this class you would like to extract in the interface. In this case, we have only one method, and that's why you see only one item here. So let's click Next. There you go, we got an interface here, and that is automatically implemented by Shipping Calculator class. So this way you don't have to manually go and type it all. I just did it before because I wanted to show you how to create an interface from scratch. In the next lecture, we'll see another use case of interfaces, and that is for increasing extensibility of an application. I hope you enjoyed this lecture, and thank you for watching. In the last lecture, you saw how we used interfaces to improve the testability of our application. In this lecture, we're going to see how interfaces help with extensibility of our application. So similar to the last lecture, we're not going to have any slides here. So let's jump into Visual Studio and start coding. Okay, let's say we would like to create a tool for migrating a database. We can start by creating a class called dbMigrator. This class can have a single method called migrate, which can be void And here we're going to have details of migrating the database. Now, to keep things simple, I'm not going to implement that here. But what I want to show you is how we can create extensibility points here by using interfaces. For now, let's just assume that we would like to log some messages on the console as the database is being migrated. For example, we may want to display the time the migration started. We may display the time migration finished. If there were any problems along the way, we can display them on the console. So one way to implement something like that is to go here and say console.writeLine migration started at, and here we can have the current date time. Potentially we can have another console.writeLine here to indicate where migration finished. Now the problem with this kind of implementation is if tomorrow we decide to use a file or a database instead of the console, we have to come back to this method and change it, which means this class has to be recompiled and redeployed. Let me tell you something interesting here. In an ideal world, we would like to design our software such that we can change its behavior without changing its code. You might wonder, how is that possible? Well, it is possible by using extensibility, which means instead of changing the code in the existing classes, simply add in new classes that change the behavior of the system. With this way of thinking, every time we want to change the behavior of our software, we create new classes, and as you learned from the last lecture, we can write unit tests or any kind of automated tests only for those new classes. The impact should be minimal to zero on the existing classes because we are not changing the existing code. Now, as much as this idea sounds beautiful, sometimes it's a little bit costly to implement. So, in practical terms, we cannot design software such that every change can be implemented using an extensibility mechanism. Well, it is possible, but sometimes the cost of that is way too much and it's really not worth it. But in this case, in our DB migrator, it is possible that someday in the future, we may decide to log messages in a file or in a database, as opposed to a console. So how can we design this DB migrator such that it's extensible? Well, that's by using an interface. Let's see how we can make this happen. So instead of using the console directly here, we should use an interface like logger. Let's create an interface for that first. So public interface iLogger. Note that I'm prefixing that with capital I. Now a logger may provide methods like log error, which gets a message, or another method like log info, which is for simply logging information messages which are not for reporting problems in the code. It's purely for troubleshooting. Let's put this interface in a separate file to clean up our code. So back here, Alt and Enter, Enter. Okay, now back to the program. And I'm going to do the same thing with DB Migrator. I'm going to put it in a separate file. So Alt and Enter, Enter. Now we want to change DB Migrator to get an iLogger interface. So as you learned in the last lecture, we need to create a constructor here. And in the constructor, we inject that interface. So iLogger, we call it logger. And with ReSharper, we can press Alt and Enter here when the cursor is on the logger here. And Enter again. And ReSharper automatically creates a private read-only field of type iLogger. So the technique we're using here is called dependency injection, which means in the constructor, we are specifying the dependencies for this DB Migrator class. And later in the main method, as you will see shortly, we are going to specify a concrete class that implements that interface. So this whole thing is called dependency injection. Now, in the migrate method, instead of directly talking to the console, we are going to talk to a logger. So say logger.loginfo, and I'm going to cut this message here and paste it here. Except that I need to change this comma to plus because I have to concatenate them to form a string, whereas in the console.writeLine, we were passing multiple arguments. Let's remove that. And I'm going to repeat the same thing here. This time I change started to finished. Again, to refresh your mind, remember the analogy I used for the restaurant. I said the restaurant needs a chef. Now, whether that chef is John or Steve or Mary, it doesn't matter as long as that chef has some capabilities to a given standard. It's the exact same scenario here. So DB Migrator doesn't care who's the actual logger. An instance of any class that implements this interface can be passed in the constructor here. So there is no coupling between DB Migrator here and that concrete class. Now let's create a concrete class that implements that interface. So public class, let's call it console logger because we use console for logging. iLogger, not the red underline, that's because we have not implemented the interface yet. So we press Alt and Enter and Enter. Now here I'm using ReSharper, so it opens up this dialog box which allows me to choose which methods I would like to implement. And by default, both of them are checked. If you don't have ReSharper, I think Visual Studio automatically implements all methods in the interface. So let's just go with the defaults. So for login error, I'm just going to use console.writeLine and pass that message here. And to make it a little bit more user-friendly, we can perhaps change the color of the font. So say console.foreground color equals console color dot red to indicate an error. We can repeat the same thing in the log info method, and instead of using red, we can use, say, green. Now let's put this class in a separate file. Okay. Let's take one final look at DB Migrator. So look, it knows absolutely nothing about the console, and it's just talking to an interface. Now let's go to the program. In the program, we're going to create an instance of DB Migrator. So var DB Migrator equals new DB Migrator. In the constructor, I need to specify a concrete implementation of that iLogger interface. In this case, we pass a console logger. And finally, we call the migrate method of the DB Migrator. Let's run the application. There you go, we got two messages on the console. Migrate Tiong, sorry for the spelling, it's migrating, started at, here's the date time, and we had a problem here with the formatting of string. It doesn't really matter. And you see the second message, migrating finished at the date time. Now let's say that hypothetical scenario is going to happen. So we decide instead of logging messages on the console, we decide to log them in a file. Let's see how we can achieve that. So all we have to do is create a new class, public class file logger. It implements the iLogger interface, and we repeat the exact same steps here. So Alt and Enter again, and again. We got these methods here. So let's create a constructor that takes the name of the file. So ctor, maybe a path is better. And now we press Alt and Enter and again. So we got the private field here. And in the log error method, we need to create a stream writer for writing data to a file. So new stream writer. Note that this class is defined in system.io namespace as you see here. And because I'm using ReSharper automatically added the using namespace for me here. So it makes your life much easier. Back here. Now in the constructor for stream writer, I need to specify the path. So I use that private field. And the second argument specifies whether we would like to append to that file. Of course, yes. Then we can call the writeLine method and pass that message here. There is just one problem here. The problem is that this stream writer uses a file resource. A file resource is not managed by CLR or Common Language Runtime, which means we need to dispose that resource once we finish using that. The easiest way to do that is to wrap this whole block here in a using statement. So let's see what happens. I move this var stream writer inside using. And then in the using block, I move this stream writer.writeLine here. Basically, what happens behind the scene is there is an exception handling mechanism inside this using that you're not going to see. It's implemented by the compiler. So if something goes wrong, an exception is thrown or something, the compiler will make sure to close the file handle by calling the dispose method on the stream writer. Let me show you that method here. So stream writer.dispose. This method is used for freeing external resources that are not managed by CLR. When we use the using statement here, the using block, the compiler automatically includes a call to the dispose method, so we don't have to manually do that. Okay, one last thing here. Perhaps it's a better idea to add a prefix string here to specify that this is an error, because when working with a file, we don't have colors like as we did with console. So we can say error plus message. We could potentially include the date time here as well, but it doesn't really matter for the purpose of this lecture. Now, interestingly, we need the exact same code for the loginfo method here. But look, we're duplicating code, and there is a principle called dry, or don't repeat yourself. So we can refactor this and make it a little bit better. What we can do is we can create a private method, call it log. It gets a message and perhaps gets another string like message type. Let me scroll down so you can see this a little bit better. And then I'm going to move all this code inside this method. Instead of using this hard-coded error prefix here, I'm going to use message type plus colon and a space. And then I'm going to reuse this method in both log error and log info methods. So see, there's no code duplication anymore. So I'm just going to call log, pass the message, and the message type is going to be error. And we do the exact same thing here with log info. Now, even a better way to do this is to use an enumeration. So you should be familiar with enumerations, but again, I leave that to you as an exercise because I don't want to get too distracted with best coding practices in this lecture, because we just want to see how we can use interfaces to create extensibility points in our application. So I think for now, that should do the job. Let's put this class in a separate file. So I'll put the cursor here, Alt and Enter, and Enter. Good. Let's review what we have done so far. So back to our program. See, we created a DB migrator and passed a console logger instance to its constructor. And finally here, we called the migrate method. Let's take a look at DB migrator. So DB migrator talks to an interface. It doesn't know what concrete class is going to implement this interface. It doesn't really care. Now at this point, when we run the application, messages are logged on the console. We can change the behavior of the application by simply going to the main method and swapping that implementation with a different implementation. So instead of console logger, I'm going to use file logger. Specifying path. So I'm going to use // say log.txt. Actually, this may throw an exception on my machine because I'm running this in a virtual machine and I don't think there's access to the root of C drive. So I'm going to change the path to projects / log.txt. Let's run this. Note that no messages are logged in the console anymore. Let me go to the file system. So C drive, projects, look, we have a log file here. So info messages are logged in this file. You see there are 4 of them because I ran the application twice in the middle of recording. So don't worry about that, there is no bug. The first one says migration started, migration finished, and then here we ran the application again, so we got 2 more messages. So the interesting thing here is we changed the behavior of our application by simply creating a new class, as you saw here, file logger, and simply passing that to this constructor here. I did not change one line of code in DB Migrator. And this is what we call changing the behavior by extending the application instead of changing the code. In object-oriented programming, this is referred to as open-closed principle, or OCP, which states software entities should be open for extension but closed for modification. And in practical terms, that means here, this class should be closed for modification. We didn't change anything here, but this is open for extension using this extension point. Now, don't think that you always need to use an interface in scenarios like from console to file system or from file system to database. Not necessarily. That was just a simple example. In your application, you might have an application that is working on a map, like a GPS application, like Google Map, and you need to calculate the shortest distance between 2 points. You can use an interface like Route Calculator that finds the shortest path between these 2 points. Later in the future, you may come up with a better algorithm. Maybe an algorithm that is faster, maybe an algorithm that knows the traffic conditions, or whether a street is 1 way or 2 ways. You can simply create a new implementation of that interface and inject that to your class without changing the existing code. Or let's say, as another example, in your application you have some kind of encryption. Maybe you have a class that needs to use an encryption service. So in that case, you can create an interface called iEncryptor and create a class that implements that interface with a very basic encryption algorithm. Later in the future, you may come up with a better algorithm, a better encryption algorithm. Then you can simply change the behavior of your application by creating a new class that implements that interface. So you got the point. Well, that's pretty much it for this lecture. I hope you enjoyed it, and thank you for watching. One of the common misconceptions about interfaces is that they're used to implement multiple inheritance in C#. And I have seen books, videos, and blog posts that make such claim. But unfortunately, that claim is fundamentally wrong. Interfaces got nothing to do with inheritance. Let's go to Visual Studio and see what I mean by looking at a piece of code. Okay, in this project, I'm demonstrating the concept of a UI framework. So we have a class like UI control with a bunch of properties like ID, size, and top left, assuming that each UI control, like a text box or drop-down list, can share these attributes. It also provides a couple of methods like draw and focus. It's a very basic implementation. Now let's create a class called textbox. Public class textbox, and we can derive it from UI control. So in some languages like C++, a class can have multiple base classes, and this is what referred to as multiple inheritance. So we can have UI control here, and let's, for sake of discussion, say we can also inherit from size. It doesn't make sense conceptually, but just for the example. Look, we immediately get a red underline here, because in C#, this class cannot have multiple base classes. But what we can do here is to have this text box implement multiple interfaces. So we can say it implements iDraggable or iDroppable. And now we have to implement these interfaces. So Alt and Enter. There you go. Now I mentioned that interfaces got nothing to do with inheritance. Let me clarify that. When we use inheritance, for example, when we derive from UI control, basically we write all that code once here, and then we don't have to type it again. The text box automatically inherits all that code. But what about interfaces? Let's take a look at iDraggable. That interface doesn't have any code. It just includes a method declaration. Same for iDroppable. There is no code. So when we go and implement that interface in a class like textbox, we have to type that method declaration again and then actually implement it. So there is no code to inherit. There is no reusability. And that's the reason I explain interfaces got nothing to do with inheritance. On the surface, from a syntactical point of view, yes, they look like they are base classes of the text box. But this is just syntax. It's fundamentally wrong to say a class inherits from an interface. A class implements an interface, because an interface, as you see here, is simply a contract. It's saying that any class that implements this interface should have a method that is public, void, and called drop. And that's what we type here. So that's the truth about interfaces and inheritance. Unfortunately, when I started learning about C# and I came across this topic, the book I read told me that interfaces are used to implement multiple inheritance. And that statement, as I explained, was fundamentally wrong, and it took me years to really get it. For years, I was confused and frustrated thinking, how can I reuse code by inheriting from these interfaces? And the truth is, that is not possible. There is no code reusability. All we are doing is confirming to a contract. We're making sure that the public interface of our class has the methods or members as declared in the interface. So I just wanted to clarify this to you in case you come across some books, blog posts, or videos that claim interfaces are used for implementing multiple inheritance. Anyone who says that definitely does not have a deep understanding of interfaces. Interfaces are used for building loosely coupled, extensible, and testable applications, not for code reusability. But interfaces do provide polymorphic behavior, and that's what I'm going to explain to you in the next lecture. I hope you enjoyed this lecture, and thank you for watching. In the last lecture, I explained to you that interfaces got nothing to do with inheritance. But interestingly, they do provide polymorphic behavior, as we learned in the section about polymorphism. So in this video, I'm going to show you how we can use interfaces to achieve polymorphism. Let's get started. Okay, in this project, I have got a class called video encoder that is responsible for encoding a video. It has a simple method called encode, which gets a video object. Let's take a look at the video encoder class. Here's the encode method. For simplicity, we don't have to worry about the video encoding logic. But what is interesting here is that once the video is encoded, we use the mail service to send an email to the person who uploaded that video to our website. Let's take a look at the mail service. So again here, to keep things simple, we are not worrying about how to send an email, we just log in a message to the console. Let's run the application. So we are simulating that a video was encoded, and we sent a notification email to the person who owned the video. Now, let's get back to video encoder. There are a couple of problems with this class. The first one is this type dependency to mail service, which is going to affect the testability of this class. So earlier in the lecture about testability, we learned that if we want to unit test the class, we have to isolate it. So instead of using a concrete mail service here, it would be better to send an interface in the constructor and initialize an iMail service field here. But that's just one problem. There is another problem. The problem is if tomorrow we decide to have another way to notify the person who owned the video, let's say send them a text instead of a mail, or maybe both, then we have to come back to this method and change it. Which means every time we change this method, the class that contains it has to be recompiled and redeployed, and any other classes that are dependent on this video encoder, again, has to be recompiled and redeployed. And as I've always said, as software engineers, we want to reduce the impact of change in our software. So earlier in this section, I introduced you to the open-close principle of object-oriented programming. Just to refresh your memory, open-close principle, or OCP, states that software entities should be open for extension, but closed for modification. Now, we're not going to apply this principle everywhere, but there are areas in our system where we see there is potential for change, like in video encoder, we know that potentially we could send a text message to the user, or maybe we would notify them as they're online on the website. So here is an area that is going to be affected as a result of that change. Now, how can we implement open-close principle using an interface here? Well, first of all, when we design this class, we should not think about mail service. We should think in abstractions. We should think when video encoder does its job, it needs to send a notification to the user who owns the video. How? We don't know. We don't know what kind of notification. We don't know if it's a mail or a text message or a real-time notification. So video encoder should not know about that. So in this class, we need to think of a notification channel as an abstraction. And that's where an interface comes in. Because interface is just a role. It's a contract. Again, remember the example about a restaurant and a chef? A restaurant needs a chef. Anyone who can fulfill that role based on some standards can be a chef for that restaurant. We don't want the restaurant to be tightly coupled to John or Steve. So same here, we don't want the video encoder to be tightly coupled to a mail notification service. So let's see how we can use an interface to implement open-close principle here. First, we define an interface. Let's call it iNotification channel. Again, this is an abstraction. We are not talking about mail or text or whatever. Now, this is just a notification channel. We want to send a message to that channel. So here we need a method like void send, which gets an argument of type message. Let me create this class. So I move this class to a separate file. Back to where we were, and same for iNotification channel. There you go. So it's a very simple, clean interface. Now, mail could be one notification channel, or SMS could be another notification channel. So we can create concrete classes that implement this interface. So let's create a new class here. Mail notification channel. Implements iNotification channel. Alt and enter. So for simplicity, let's just log a message on the console saying sending mail. We move this class to a separate file. Back to where we were. Let's create another class that implements this interface. This time, SMS notification channel. iNotification channel. Again, the same steps. Implement the interface, log a message on the console saying sending SMS. And we put this in a separate file. There you go. So we have one interface with two implementations. Now let's go to our video encoder class. So here we no longer need a reference to mail service. We should think in terms of a notification channel. But we could have more than one notification channel, right? Because at the same time, we may want to send an email and also a text message to the person who owns the video. So what I'm going to do is let's remove this field here. Basically, we need a list of notification channels. So private, read-only, ilist of iNotification channel, and let's call them notification channels. Now ReSharper is detecting that I'm using ilist, and that's a generic interface as defined in system.collections.generic. So you can click that or press Alt and Enter. So it adds the using statement on the top here. Again, if you don't have ReSharper, you have to manually type that. Now in the constructor, we need to initialize that list. So let's just initialize it to an empty list, new list of iNotification channels. Now, all we need to do here is once the video is encoded, we need to iterate over the notification channels and notify each of them. So we do a simple for each channel in notification channels, channel.send a new message. Right? So in the video encoder, we are not talking about mail service. We're not talking about SMS. We're talking about abstractions. iNotification channel. Whoever implements that, that's none of our business. Video encoder is not going to be affected. We can create new implementations of that interface, and this class remains unchanged. So with this, we achieved open-close principle. Our software is open to extensions. We create new implementations of iNotification channel. And it's closed for modification. So this class is no longer going to be changed. Now there is just one step missing here. We need to tell video encoder about the actual notification channels at runtime. So how we do that is, because this list is defined as private, because it's implementation detail of this class and we don't want to expose it to the outside, we need to create a method here, a public void, let's call it register notification channel, which simply gets an iNotification channel parameter and call it channel. All we do here is we add that to our list. Add channel. So this is the method we use from the outside. Let's go to the program class. So in the main method, after we initialize the encoder, we call that register notification channel method. And here we pass a concrete implementation of notification channel. So new mail notification channel, and we repeat that. This time we use SMS notification channel. Now let's run the application. There you go. We got two messages. One is sending mail, one is sending SMS. And interestingly, we can create a new class that implements iNotification channel, and we just pass that here in the main. And as you saw, video encoder is not going to be affected. Now, the interesting thing here is that with interfaces, we have a polymorphic behavior. Let's go to video encoder. So when we are iterating this notification channels list, at runtime, when we call the send method, depending on the runtime type of that notification channel, a different method is going to be called. And that's what we call polymorphism. So at runtime, if the first element of our list is a mail notification channel object, the send method in the mail notification channel class will be called. This one. Get back here. Now, if the second element of the list is an SMS notification channel object, a different send method will be called. This one. So as you see, with interfaces, we can have polymorphic behavior, and that's very powerful. Now, there is also a different way to implement the exact same scenario in C#, and that is using events and delegates. And that's something that I have classified as advanced topic, which you can find in my C# advanced course. So in my C# advanced course, I introduce you to the concept of delegates, and I actually have a video on my YouTube channel called Events and Delegates, where I introduce the exact same problem, but use a different solution using an event and a delegate to implement that kind of extensibility. So in case you're passionate about learning all this stuff, that's an additional video you can look at. I hope you enjoyed this lecture, and thank you for watching. Okay, in this lecture, we're going to take a look at the stopwatch exercise. This is the code that one of my good students, Tim, has written. Hi, Tim. Thanks for sending your code. I really appreciate that because you're the first student who shared his code with me and everyone else. So you've done a really good job. In this video, I'm going to show you a few things that you can improve in this code. So let's go through what you have done so far. This is our main method. We have a loop that is executed twice. We start the stopwatch, then use thread.sleep to put a bit of delay in the application. Then we stop the stopwatch and display the interval or duration. Then we wait for the user to press enter, and then the loop is executed one more time. Let's take a look at the implementation of stopwatch. So in the stopwatch, we have a few properties: start and end time. a flag field called running that we use to check if the stopwatch is running or not. In the start method, if the stopwatch is not running, we set the start time and then set running to true. Otherwise, we throw an exception, and this is used to make sure that we cannot call the start method twice. So really good, well done. In the stop method, if the stopwatch is running, we set the end time and then set the running field to false. Good. And here we have a method called getInterval, which calculates the duration between the start time and end time. Now, what can we improve in this code? Well, the first thing I see here is that these two properties are declared as public. Remember the encapsulation principle? So the point of encapsulation is to put properties and methods that are related to a concept in a class, and preferably make those properties private, because those properties are the implementation detail of that class. We don't want to expose it to the outside world. Instead, we want to have public methods that work on those properties. We use these properties, in this case, these three properties here, to keep the state of stopwatch. We don't want the consumers of this class, in this case, this main method, to mess up with the state of stopwatch. We want to limit how this class is used. Remember the black box metaphor or the DVD player? A DVD player has a few buttons on the front, which gives you limited access to what you can do with it. Imagine if the circuit boards and ICs of the DVD player was accessible. What could have happened? So that was the theory part. Now let's take a look at the practice. The reason we shouldn't declare these two properties as public is this. Let me show you. So here we start the stopwatch, and now because I have access to those properties, start time, I'm gonna set that to tomorrow. And also, similarly, I can set the end time to last year. So see how I'm messing up with the state of stopwatch here? It starts tomorrow, but ends last year. Let's run the application and see what happens. So this is the duration. It doesn't make sense. So what we want to do is to declare these as private. And in fact, we don't even need a property here. A field is sufficient because we're not going to provide get or set access from the outside. So I'm going to get rid of these get and set here. Similarly here. And now because we converted these properties to a private field, we need to modify their name to match the standard naming convention, which means they should use camel notation and be prefixed with an underline. So with ReSharper, I can immediately fix this. Alt and enter, enter. If you don't have ReSharper, you need to do it manually by hand. So let's try it here. Underline, end time. And note that now these two properties are not accessible from the outside. So I cannot mess up with the state of stopwatch. Good. Now, this running field, I want to put it close to other fields just for clean coding. And in terms of naming convention, it needs to be prefixed with an underline. Now, I'm not going to add this underline here because the problem with that is, look, I broke my code. I have to modify all these references here. That's why we use ReSharper. So with ReSharper, when you press Alt and Enter here, ReSharper automatically fixes all references to that private field. Also note that you don't need to initialize it to false because Boolean fields by default are initialized to false. And that's the reason this false keyword here is grayed out. So I'm going to remove that again with Alt and Enter. Enter. There is another interesting scenario here. Our start method takes a date time. So again, with this, I can mess up with the state of this class. How? So I go here. Instead of sending now, I'm going to send tomorrow. And similarly, in our stop method, I'm going to send last year. See, this is exactly like the code I wrote before when I access those properties directly. We don't want to mess up with the state of our classes. The class should always be in a valid state, which means these methods should not take a parameter. They should use the current date time. So what I'm going to do, I'm going to remove this parameter. Instead, use datetime.now. Similar in the stop method. And I'm going to use datetime.now. Note that end time is not compiled. And the reason for that is because I manually changed it to underline with a lowercase e. That's why I say you should use ReSharper as much as you can, because it really helps you with your coding. So all these little things don't get along the way and waste your time. So what I'm going to do is to quickly fix this. Alt and Enter. Change all end time to underline end time. So I corrected both these references together. Now let's get back to the start method. This method is perfectly fine, but conventionally we often do validation at the beginning of a method. So when someone reads this code, they can see what are kind of exceptions that this method can throw. So I'm going to reverse this if else. I'm going to say if it's running, throw an exception. Otherwise, do this. Now, note that ReSharper has grayed out this else block here. Why is that? The reason is, if the stopwatch is running, we throw an exception, so this part of the code is never going to get executed. Which means we don't really need to add this else block here. If the control gets here, that means running was false. So this way we can get rid of an extra else and make our code a bit cleaner. So now put this back here and get rid of these extra spaces, and we don't need the braces either because it's just one line. The code is shorter and cleaner. We could do a similar technique in the stop method. So if we call the stop method when the stopwatch is not running, we could throw an exception. So this time we say if it's not running, I'm going to copy paste this line here and change the message. That's it. Otherwise, we get here and we change the state of our stopwatch. Okay, finally, get interval method. That's perfectly fine, but I just want to give you a quick tip here to make this a little bit shorter and cleaner. It's obvious that this method is returning interval or duration. So there's really no need to declare a separate variable and then return it immediately. If we were going to use this variable multiple times in that method, it made sense. But now it's kind of redundant. So we can get rid of that, which means the method is now only one line. And it's pretty clear. End time minus start time, and that's the interval. Okay? Okay, now let's take a look. So now that I've removed those parameters from start and stop methods, we cannot mess up with the state of stopwatch. So we remove this. And similarly here. One more tip I would like to give you here is we don't need to do a loop here to call thread.sleep of 1 millisecond 1,000 times. So we can simply put 1,000 here, 1,000 milliseconds, and get rid of an extra for loop. Now we stop the stopwatch. We display the result. I would like to add a bit of message here. duration, and then before console.readline, I would say press enter to run the stopwatch one more time. It's really not required. It's not part of the exercise. It's my personal preference. Your code is perfectly fine. And one more tip here is console.writeLine method always calls toString on any object passed to it. And that's the reason this toString here is grayed out. So we can get rid of it, make the code shorter. And now let's run the application. So duration is 1 second because we had a delay of 1000 milliseconds. And here's a message. Press enter to run the stopwatch one more time. And here's a new duration. Okay, that's pretty much it. Again, thanks Tim for sending me your code and sharing it with others. I hope you and everyone else who watched this video learned something new and that would make you a better developer. Thank you for watching. Okay, in this lecture, we're going to look at the stack exercise. This code is written by one of my good students, Martin. Hi, Martin. Thanks for sending your code. You've done a really good job. I'm just going to tweak a couple of things here to remove the bug that you told me about and make the code a little bit cleaner. So basically, the bug that we have in this program is if we start pushing numbers from 0 to 5 to the stack and then popping them, the program works. But if we start from 1, it doesn't. Let's give it a try. So let's start from 0 to 5. So as you see, numbers 5 to 0 are popped from the stack. So the program is working properly. But if you change this to 1, let's see what happens. So instead of getting 5, 4, 3, 2, 1, 0, we got 5, 3, 2, 1, 1. What's going on here? Let's take a look at Martin's implementation of stack. So here is how Martin has implemented stack. He has a private list of objects, which is really good. So we're using object here to make sure we can store any object in the stack because object is the parent of all classes in .NET. So well done, Martin. In the push method, here we check if the object that is being passed is null. And if that's the case, we throw an exception. Really good. Now here is some logic for adding that object to the stack. We're going to explore this in a few seconds. And here we have a pop method. So first we check if the stack is empty, then we do not allow the client of this class to pop any objects. So we throw an invalid operation exception. Really good. And here is the logic for removing the object and returning it. Now, why do you have this bug in this class? Well, what I see happening here is first, we add that object in the list. And then I'm guessing with this logic, we're trying to move the objects in the list one to the right. I don't think this is really necessary. All you need to do is to add that object to the end of the list. So I think this code is really not required. So I'm going to delete this. So with this code, we simply add that object to the end of the list. Similarly, let's take a look at the pop method. So here we get a reference to the object that we should return. And then we move items in the list, one to the left or one to the right. I'm not quite sure what's happening here. And then finally, we remove that object from the list. Again, I think this code is really not necessary. We don't need to move objects in the list. So I delete this. Instead of the remove method, I'm going to use remove at. Remove at gets an index. So remove at. Now, what is the index of the object that we want to pop? That's the last item in the list, right? So that's going to be list.count -1. Here we have -1 because the index of the first item in the list is 0. We also need to change this. So the object that we want to return is the last item in the list. Again, list.count -1. Now I want to add a vertical line break here because when lines are close together, that means they're related. When I first saw this code, I thought all these 3 lines together represent one concept, but that's not the case. Only this if and here the throw exception are related. Another thing we can do to improve this code is we have repeated this list.count -1 twice. So we can extract that into a variable. So what I'm going to do with resharper, Control-Shift-R, introduce variable. And I'm going to replace two occurrences. So we just call it index. So that's the index of the object that we want to remove and return. Also, instead of using int, we can use var. And similarly, instead of object, we can use var. Now note that the naming convention for local variables in C# is camel notation, which means the first letter of the first word should be lowercase. Also, resharper is suggesting that here, so take a look at this icon here. We can activate that by pressing Alt and Enter. Resharper is suggesting to rename it to match the standard naming convention. So I'm going to go ahead with that. Okay, I think we're done with this method. There is nothing else we want to do in the add method. So far, so good. I see a green underline here, and that's because resharper is suggesting to make this list read-only. The reason for that is we don't want to accidentally reinitialize that list anywhere else in this class. So I'm going to put the cursor here. Alt and Enter with resharper. Now the stack class is finished. Now let's run the application. So note that the bug is fixed. We get 54321. And if I change this to 0 to 5, it still works. 543210. Is there anything else we can do to make this code better? Well, we can change this stack here to var, because look, it's already repeated here. So it's obvious that it's of type stack. So I put the cursor here, Alt and Enter. Note that underline is used to prefix private fields in a class, and we shouldn't use it in naming our local variables. And if you note this icon here, even resharper is suggesting that. So with resharper, Alt and Enter. There is one last thing that we need to add to the stack class that was part of the exercise requirements, and that's the clear method, which removes all objects in the stack. So I'm going to go here, public void clear. All we do is to call the clear method of our list that internally represents the objects in the stack. Now we can test that. So here we push 5 objects in the stack. Now we clear the stack. And when we get here, we should get an exception because the stack is empty and we cannot pop anything. So let's run the application. There you go. We got an exception of type invalid operation exception. That's it. Again, Martin, thanks for sending me your code. I hope you enjoyed this video and learned something from it. Thank you for watching. Okay, so this is the source code that Igor has sent me. Hi Igor, thank you very much for sending me your source code. You've done a great job. Let's go through what you have done so far, and then I'll point out a few things that you can improve here. So I noticed you declare this interface called iWorkflow with a method called execute. And then you have different classes that implement this interface, like video uploader, call web service, and so on. And you also have a workflow engine, which has a list of iWorkflow. It exposes 2 methods for adding a workflow object using that interface and removing a workflow object. And finally, it has a run method that iterates over the list of workflows and executes them. And in your main method, you simply instantiate a workflow engine, add different workflow objects, and run it. So what I like about your implementation is the loose coupling. So I see your workflow engine is not tightly coupled to implementation of your actual workflow objects like change status or send email. It purely talks to an interface, iWorkflow. So great loose coupling. Now let's see what we can improve here. The first thing is this change status or send email is not really a workflow, because a workflow is a collection of tasks or steps or activities, whereas each of these classes represent only one step. So a better name for this interface would be iTask or iActivity. If you look at the description of the exercise, let me open it up here. So take a look here. Here it says a workflow is a series of steps or activities. The workflow engine class should have one method called run, which you have done perfectly, that takes a workflow, which means a collection of tasks. So the first thing I would suggest to change here is renaming that iWorkflow to iTask, and simply with ReSharper, iTask. Okay, now let's take a look at our iTask. So task has a method called execute. So each task can be executed. Perfect. Now we need a separate concept for the workflow, because a workflow is a collection of tasks. So what I would do here is I would declare an interface called public interface iWorkflow. Now we should be able to add or remove a task from workflow. So these methods that you have in the workflow engine really belong to the workflow itself. The reason I prefer to take them out of the workflow engine is because in the real world, a workflow engine is far more complex than what we have for this exercise. For example, in your workflow, you might do exception handling, you might do logging, you might persist the state of your workflow. Let's say your workflow has 10 steps and it needs to go in a hibernate mode after the third step, because it's going to be a delay until we hear back from the fourth step. So you need to be able to persist the state of the workflow in some kind of persistent store like a database or file or whatever, and then rehydrate the workflow from that later. So I would prefer to take these methods out and make this engine purely responsible for executing a workflow. So what I'm going to do is in workflow, I'm going to introduce two methods, add a task and remove a task. Why is it complaining? Okay, the problem here is says inconsistent accessibility. Parameter type iTask is less accessible than method remove. What this means is because we declared this task without an access modifier, in this case public, by default is assumed to be private. So we cannot declare a public interface that uses a private interface. We need to make this public. Right? Now, let me implement a basic workflow class. That of course should implement iWorkflow. With Alt and Enter, we implement the members. Now what you had here in your workflow engine is pretty much what we need to push into the workflow class. The concept of a list of tasks and adding or removing tasks to it. So I'm going to cut this. And well, we already have that here. Let me just temporarily paste it. We need to change the name of the constructor to match the class name. So copy, paste. So that's my list of tasks. Also, it's better to use a different name than T. The first thing that confused me when I saw T here, I thought you're working with a generic type. And T is a common convention to represent generics in C#. If you're not familiar with generics, take a look at my C# Advanced course. That's the first lecture in that course. Now I'm going to rename this to underline tasks. Now we have a green underline here. ReSharper is suggesting to make this field read-only. And I think I have explained the reason for that in my course. Let's make it read-only first. The reason for that is we initialize it here in the constructor, and we don't want to accidentally reinitialize it because that list can already have some objects in it. We don't want to accidentally lose those objects. All right, so what you had in add workflow object, I'm just going to move to this add task. And instead of iObject, we're going to call it task. So I'm thinking you probably come from C++ background because I see you have used the Hungarian notation here. but that's not a common convention in C#. So we don't prefix the name of our objects with their data type. Now let's remove this method. I'm going to remove your implementation from this method, remove workflow, to remove task here. And of course, we want to change my object to task. And finally, I'm going to remove this method. All right, now let's revisit this. So we have a workflow class, which implements iWorkflow. It has a collection of tasks, and you can add a task to it or remove a task. Again, if you look at the exercise description, that's exactly what we wanted. A workflow is a series of steps or activities. One more thing we want to change here is, let's go to your workflow engine. All right, this class is not going to compile now. First, let me make it public. Run method should get a workflow and run it. So iWorkflow, that's it. Now here we need to access the list of tasks that workflow represent. So we need to go to workflow class. And here we need a separate method for returning the list of tasks. I'm going to use the IEnumerable interface, and I'll explain that shortly. Get tasks. Simply return tasks. Why did I not use the list class? The list class, as you see, has methods for adding or removing a task. I don't want the caller or the client of this class to work directly with the list that this class is internally representing to hold its tasks. This is the implementation detail of my workflow. That's the reason we added these public methods here for the client of this class to use to add a task to this list. If we expose the list here instead of IEnumerable, the client of this class can go directly in this private list here. In this particular example, it makes absolutely no difference if we call the add method, like here, or get a reference to underlying tasks and call the add method on that. But you could have scenarios, for example, you could do some kind of check-in in your add method. This way, you definitely do not want to expose your private list, which is the implementation detail, to the clients of this class. You want to make sure that they go through this add or remove method because some magic is going to happen. And this is all about encapsulation that I talked about in the course. All right, now that we have a method to get a list of tasks, and by the way, the return type is IEnumerable. So if you take a look at IEnumerable, it's simply an interface that is defined in system.collections.generics. iTask. Let's just declare A here. Look, it does not have a method like add or remove. It's purely an interface that allows us to enumerate a list. That's it. So this way you return a read-only version of your internal list. All right. Now let's get back to our workflow engine. So here we tell the workflow.getTasks. Okay, this method is not declared in the iWorkflow interface, and that's why it does not appear here. So see, we added that in our workflow. It's here, not in iWorkflow. So what I'm going to do, copy this bit, paste it here. That's it. Now let's go back to workflow engine. That's our run method now. Takes a workflow and iterates over its tasks and execute each. Very, very basic. In a real world scenario, perhaps you might want to surround this with a try catch block. So something like try, run this. And if there is an exception, you would probably want to do some kind of logging and maybe terminate the workflow, terminate and persist the state of the workflow, something like that. And then later you may get that workflow and resume it. It's beyond the scope of this exercise, so don't worry about it. It's just to give you some idea. Now we still have some minor errors on this page because it's not going to get compiled, as you see indicated here. So let's jump up here. Of course, we change our workflow engine, the name of methods. So here, instead of calling the add workflow object and workflow engine, we need to call that on the workflow, not the engine. So I'm going to change this to workflow. And of course, here as well. And I'm going to change all of these methods in one go to add. Now finally, we need to create a workflow engine. So I'll call it engine, new workflow engine. And then I call the run method and pass my workflow. And it's better to change this to var, make the code a little bit cleaner. That's pretty much it. Let's run the application. So each task was executed, uploading a video, calling web service, sending an email, and status changed. That's pretty much it. Again, thank you very much for sending your source code and sharing it with others. You've done a great job, and I'm happy to see that you've really understood the concept of loose coupling. We just had to move those add and remove methods from workflow engine to the workflow class. I hope you enjoyed this video, and thank you for watching.